Yeah, good evening. So please type in the chat box. Is the audio and video fine to all of you? Not visible? But is the audio coming? Is it audible? It's audible, but it's not visible. Okay. Now all clear? Let me check one. Let's reload the video. Yeah, I think now it's all clear, right? Just a second. Okay. All okay? Good. Great. Okay. So let's start this new module, turbo machines, of course. Okay. Chalo then. And of course, in today's class, basically you might have seen the planner. So basically what I am planning to do is like पहले हम fluid mechanics का जो basics होते हैं Reynolds transport theorem, okay, and then after simple applications to like linear momentum and angular momentum, okay, और उसके बाद dimensional analysis का थोड़ा सा basically idea लाना है. So these are the basic things that I'm going to cover in today's class. Okay, I think Shivam sir might have covered all of these things to you. But we'll generally have a quick review of this Reynolds transport theorem and then dimensional analysis like the Buckingham spy theorem, okay, which is much important generally when you talk about turbo machines, okay, because in reality when you are doing experiments on turbo machines, it's not possible to construct a very large scale turbo machines, okay. So what we'll do, we'll generally decrease the size and construct a small model accordingly. So in this particular class, we'll have a quick revision of all these things, okay, like whatever the things. Voice nahi aa rahe, volume is low. Is volume, my god, what's happening today, just a minute, I'll convey the team. Maybe my phone is somewhere here. Yeah, just a minute, we'll convey the team. Yeah, they're checking the volume. Good. But I think voice is full. Hello, just increase the voice. Yeah, okay, now it's fine, all is well. लेकिन कुछ लोगों को दिक्कत आ रहा है. I think it's fine. Okay, so yeah, basically what are the topics you have done already in fluid mechanics today? So that's going to be the basic revision, like the Reynolds transport theorem, okay, and then after applying this to linear momentum, so basically where it's basically impact of jets actually, which many of you might have seen again during the control volume analysis chapter, and then after we'll talk about the dimensional analysis, okay. So these are the things. So before I go forward, many of you might have seen me sometime in the past, maybe when I'm teaching the crash courses on YouTube for fluid mechanics last year, or the maths for XC, all these things. But for who don't know me, I would like to just give you a quick introduction. So before PW, I was working in BRC, Baba Atomic Research Center basically. I was posted at Hyderabad, NFC Nuclear Fuel Complex. And before that, before going to BRC, I was working with HPCL, Hindustan Petroleum Corporation Limited, okay, which again, I think recently one advertisement is also live. Some of you might have applied for that. So I was working with HPCL, and then I went to BRC, and then later I have come to PW, of course, okay. And of course GATE, I have all India rank 4. There are many, of course, comma 10, we have 40 one time, okay, 22, we have a lot of numbers, but that's okay. This is the best out of all those things. And I've been teaching GATE for 7+ years. Normally I generally work out at basically for past 7 years I am teaching subjects like thermodynamics, fluid mechanics, heat transfer, okay, then this turbo, applied thermodynamics, all these things, and then of course mathematics as well. And before this, 2 years in the beginning of before starting GATE syllabus, 2 years before, I was teaching JEE advanced maths actually, okay. So that's how it lined up. So चलिए इस लेक्चर पे हम पहले टर्बो मशीन्स का डेफिनेशन देखते हैं, okay, then we'll see the broad classification of turbo machines. So there are a lot of classifications again, so depending on working fluids, depending on the type of the machine basically, okay, सारा क्लासिफिकेशन है. So involves transport theorem, RTT and applications and basic terminologies as well. Okay, so we'll look at some basic terminologies and of course जब time permit होता है तब हम dimensional analysis के बारे में भी देखेंगे. ठीक है, so that's how we'll do that. तो मैं हिंदी मीडियम से हूँ, कोई दिक्कत नहीं. I'll try to do my best in हिंदी, but trust me, I'll try to do my best. Okay, चलो let's start. So turbo machines. So basically, you know, any machine that converts stored energy in fluid to mechanical work, or vice versa. वाइस वर्सा मतलब मैकेनिकल वर्क से फ्लूइड में एनर्जी स्टोर करते हैं. ओके, सो लेट्स सी. सो बेसिकली देयर आर टू सेट्स ऑफ मशीन्स व्हिच वी डील. स्टोर्ड एनर्जी इन फ्लूइड एंड मैकेनिकल वर्क. सो जो मशीन्स फ्लूइड से एनर्जी लेके मैकेनिकल वर्क प्रोड्यूस करते हैं उनको टर्बाइंस बोलते हैं. ठीक है, और जो मशीन्स मैकेनिकल वर्क लेके एनर्जी इन द फ्लूइड दे आर कॉल्ड एज pumps, or basically you can say the other parts. Okay, so basically we have so many like pumps, compressors. Okay, then we have fans, you know, blowers. We'll see all these things. Okay, hoods, blower, all these things in detail as we move along this course. But in this case, both of them अदा किया है, there will be any problem, it's okay, no issue. I'll try to teach all the basics which are necessary. Okay, so but I think all of these things might have been covered already in fluid mechanics, so just like a revision. Okay, so now let's see. This is basically the turbo machines. Like many of you might have seen some names. आपको भी कुछ नाम्स पता है already. So examples like Pelton wheel, hydraulic machines, or let's talk something like hydraulic machines or hydraulic turbines जो पानी से काम करता है. Then steam turbines we have. Normally we deal the steam turbines much in Rankine cycle as well, correct? So जब हम Rankine cycle के analysis करते हैं, एक boiler लगा के water को steam convert करके, and then we'll send the steam into the turbine, obviously, correct? So then we have gas turbines. Normally जो airplane वाला gas turbines. मान लो कि आपने एक एयरक्राफ्ट और लेकिन किसी गैस पावर प्लांट देखा था तो उसमें गैस टर्बाइंस आते हैं. एंड देन कंप्रेसर्स, पंप्स, फैंस, ब्लोअर्स, यू हैव लॉट ऑफ स्टफ. ओके, विल डील ऑल दीज थिंग्स इन डिटेल वीक बाय वीक, ऑफ कोर्स. ओके, एंड नॉर्मली इफ यू गो फॉर क्लासिफिकेशन, देयर आर मेनी क्लासिफिकेशंस. लाइक जब मैंने कहा था नॉर्मली हाइड्रोलिक मशीन्स, देन basically steam turbines, or basically in hydraulic machines you can again classify. In hydraulic machines we can classify as turbines, and we have the other parts like pumps, compressors, these things. Okay, pumps, compressors जो power producing वाला and एक power consuming वाला. So pumps, compressors, then उसके बाद like fans, blowers, you have a lot of stuff like this. Okay, so these things, blowers, all these things. And depending upon the working fluid, like again in turbines you can go for gas turbines. Then again depending upon the compounding techniques like pressure compounding, velocity compounding, we have a lot of things. Okay, then let's see. This is one thing based on fluid. Okay, then again based on principle of operation, based on principle of operation, based on principle of operation, we have something like impulse machines. हम इस क्लास में नहीं लेकिन कल की क्लास में पढ़ेंगे कि impulse machines क्या होता है, reaction machines क्या होता है. ओके, फिजिकली फंडामेंटली डिफरेंस क्या आता है इन दोनों में. ओके, सो विल लुक एट दैट, impulse machines and reaction machines. ठीक है, and normally we have, as I told you, this classification is very naive classification because मान लो कि आपने classification करना चाहते हो, there are many ways you can classify these machines actually, okay, depending upon stages, a lot of things, okay, but we'll keep it as simple and short as per the GATE and ESA syllabus levels, okay. So let's see then Reynolds transport theorem. I hope this is already covered in your fluid mechanics, in your control volume analysis, लेकिन मैं अब एक थोड़ा सा आइडिया देता हूँ. So मान लो कि if there is a property B, if B is a property of the control system, if B is a property of a control volume, actually here property of B is an extensive property, let's say B is an extensive property of a system, and what is system? Basically system is generally in terminologies you might have seen control mass. Control mass इसका मतलब क्या है? Mass is constant, okay, of a system. Then dB by dt of the system is equal to dou by dou t of integral over the control volume beta times rho dV plus double integral over the control surface S beta times rho v r bar dot n cap ds. So this is the Reynolds transport theorem, of course, correct. So मेरा सर के ऊपर से जा रहा है. Why? This was done right already. This isn't done. अरे निहारिका का boyfriend, oh my god, nice. You haven't seen this normally in fluid mechanics. It would have been done right in control volume analysis. Right? No? Okay. Okay, got it. Fine. Let's see. Fine. ठीक है, कोई दिक्कत नहीं, मैं स्टार्टिंग से पढ़ाता हूँ, कोई दिक्कत नहीं. No, no, no. Okay, fine, fine, fine. Okay, no issues. So see here. ठीक है, मैं एक्सप्लेन करता हूँ. देखिए, I'll show the derivation, but I think normally I have taught this in one of the English batches, of course. Control volume analysis. I'll show you so that you can have some idea. Control volume analysis, yeah. ठीक है, मैं दिखाता हूँ, कोई दिक्कत नहीं. Recap of previous lecture. So एक लेक्चर पहले जाना है. You might have solved these questions, no? इस क्वेश्चन आपने सॉल्व किया था. मान लो कि एक जेट जाके एक प्लेट को हिट कर रहे. We'll on slide map it's okay, but पहले ये कंफर्म कीजिए, ऐसे क्वेश्चन सॉल्व किया था आपने? नो? हाँ ना कुछ? यस. तो बिना रेनॉल्ड्स ट्रांसपोर्ट थ्योरम के साथ कैसे सॉल्व किया आपने इस क्वेश्चंस को? ठीक है, करेक्ट. व्हेन यू हैव सॉल्व्ड देन यू माइट हैव सॉल्व दिस रेनॉल्ड्स ट्रांसपोर्ट थ्योरम. ठीक है, फाइन. सो लेट्स सी. I'll just show you and explain you. ये पता है सबको? ये पता है फर्स्ट प्रिंसिपल ऑफ डिफरेंशिएशन, df by dt इज इक्वल टू, क्योंकि टू बी फ्रैंक गाइस, टर्बो मशीनरी ऐसा एक सब्जेक्ट है कि जो फ्लूइड मैकेनिक्स की बेसिक्स पे बिल्ड करते हैं. ठीक है. सो हैव यू सीन दिस df by dt लिमिट डेल्टा t टेंड्स टू 0 f of t plus dt delta t minus, yeah, correct. So let's see this. When you have this control volume then, okay, so मान लो कि ये एक कंट्रोल वॉल्यूम है. ठीक है. सो वेन एवर देयर इज ए फ्लूइड फ्लो, एंड मान लो कि आपने अगर फ्लूइड की एनालिसिस करना है तो इस फ्लूइड में हम एक वॉल्यूम सेलेक्ट कर सकते हैं. ठीक है. एंड इस वॉल्यूम विथ टाइम इट मूव्स ऑब्वियसली. ओके, मान लो कि आपने एक रॉकेट का इंजन लिया था. ओके, देन व्हाट हैपनिंग, आर इट नथिंग बट इट्स रिलेशन बिटवीन सिस्टम एंड कंट्रोल वॉल्यूम. या ऑफ कोर्स. ओके, सो डायरेक्ट फॉर्मूला. ओके, लुक, सो बेसिकली इस कंट्रोल वॉल्यूम, दिस moves actually with time. Okay, so when this control volume is actually moving with time, then what happens when this control volume is here? मान लो कि जब fluid है, we fixed some volume, so in this volume there are some particles at time t. Okay, so what happens at time t, if you identify a region, then there are certain particles at time t. Now if you fix the same control volume, then the mass which is inside this control volume at the given time is actually the system. Okay, so system is always defined by set of particles. Clear? So when I call it something as a system, then I mean I have placed some particles and that particles will not leave the definition of the system actually. Okay, but what happens when this is control volume, this is the control volume and this has some particles at time t. So I have written here control volume at time t. Okay, now when time progresses, when time goes to t plus delta t, what happens? These particles will actually move because there is flow happening. So ultimately the particles which are in this volume at time t, these particles will now move out at time t plus dt actually, of course. Okay, then in such case the property value in this region will change. Okay, because मान लो कि पहले इस volume पे there are particles which are at temperature, let's say 300 Kelvin. Okay, but now when there is flowing, it can happen that these particles at 300 Kelvin they flow out and some new particles will definitely come in because flow is happening continuously. Okay, when new particles are coming, new particles need not be at 300 Kelvin. Okay, so there is certain amount of difference that happens. Now because of that difference in the particles which are entering, there is always some property that changes in this particular control volume actually. Okay, so which is given by this value. So dB by dt of the system is equal to given by this limit because of this first principle. Then after you do a bit of mathematical analysis, okay, mathematical building up of integrals and all, you will get this result which I have seen. So here you will see this dB by dt of the system is called rate of change of property B of the system. B of the system actually here. So this is rate of change of property of the system, and this tells you rate of change of property of the control volume. Of the control volume. See, when these particles are initially here, so let's see, when these particles are initially here, which is the system, basically my system is set of particles. When the particles are initially here, the particle have some properties, but because of the motion, like for example you take pressure or basically any extensive property, let's say like something like momentum, okay, then it's not guarantee the particles velocity in this region and in this region is same. मान लो कि there is a sudden diversion or sudden contraction of the pipe, then what happens? The velocity of the particles here and here will not be same. Okay, so the particles velocity get changed. So because of which the momentum of the particles can change actually. Okay, so when the momentum of the particles gets changed, then ultimately this, first of all, because of the particles leaving this control volume and new particles entering, there is some change of quantity in this control volume. At the same time, there is also change in quantity of these particles because of the flow. So these two are actually connected by RTT, Reynolds transport theorem, and this statement and this is basically the net rate of efflux or net rate of efflux, you can say, basically crossing the control surface, crossing the control surface actually. So सबको न्यूटन थर्ड लॉ पता है? बताओ एक बार, न्यूटन्स थर्ड लॉ ऑफ मोशन, ये क्या होता है? Newton's third law of motion. Many people might have thought that सर मैंने जेट स्ट्राइकिंग ऑन दिस प्लेट बहुत आसान से सॉल्व किया था फ्लूइड मैकेनिक्स में, लेकिन अब इसकी जरूरत क्या है? रेनॉल्ड्स ट्रांसपोर्ट थ्योरम का जरूरत क्या होगा? ओके, सो नाउ टेल मी व्हाट इज न्यूटन्स थर्ड लॉ ऑफ मोशन? जो स्टेटमेंट आपको पता है वो पता ही है बस. सर एवरीथिंग इज बाउंसिंग, कोई दिक्कत नहीं. सी, try to learn, it's okay. I think using vectors, integrals, these things are making you panic, but no issue. Action have equal and opposite reaction. Every force has an equal and opposite reaction force. Good. Okay, so I'll ask you one thing. Why I'm teaching Reynolds transport theorem, I'll tell you. What is the conceptual mistake that's in people's mind? I'll tell you. Look, normally मान लो कि मैंने एक वॉल्यूम लिया था, ठीक है, एक वॉल्यूम लिया था. लेकिन इस वॉल्यूम में कुछ नहीं है, सो मास इज 0 ऑब्वियसली, बस इट्स एन एम्प्टी स्पेस, दैट्स इट. ओके, देन व्हेन यू से न्यूटन्स थर्ड लॉ ऑफ मोशन, पहला चीज ये है कि आई वांट टू क्लैरिफाई टू थिंग्स. सो फर्स्ट थिंग इज every action has equal and opposite reaction. This is what people tell you, correct? Every action has an equal and opposite reaction. This is what people tell you, okay? And स्कूल्स में एग्जाम्पल भी देते हैं कि मान लो कि आपने एक बॉल लिया था एंड इस बॉल में एक वॉल को हटाता, तो देन बॉल विल कम बैक. ओके, देन व्हाट डू यू अंडरस्टैंड बाय दिस? पीपल टेल यू दैट going of the ball is action and coming back of the ball is a reaction, correct? This is what people tell you. Now मैं ये पूछता हूँ कि मान लो कि मैंने मेरा मोबाइल लिया था, okay, and if I throw mobile onto the wall, will I get my mobile back to my hand? Will I get my mobile back to the hand? No. No. क्यों नहीं आएगा? ठीक है, नहीं आएगा, बढ़िया है, लेकिन क्यों नहीं आएगा? ट्राई करके देखो, पक्का आपकी मोबाइल फोन पे भेजिए, मतलब पोस्ट पे भेजिए, करेक्ट? इट वोंट कम. नाउ द क्वेश्चन इज व्हेन बॉल इज कमिंग, व्हाई फोन इज नॉट कमिंग? मटेरियल. न्यूटन ने मटेरियल के बारे में कुछ नहीं बताया. अगर न्यूटन लॉ में है क्या, for every elastic isotopic material action has equal and opposite reaction. मटेरियल में डिफरेंस है क्या? न्यूटन थर्ड लॉ में किसी की जगह पे मटेरियल का स्पेसिफिकेशंस दिया क्या हमको? नहीं, करेक्ट? ठीक है, जो लोग आप प्रॉपर्टीज बताए वो न्यूटन ने नहीं बताया. शेप ऑफ द बॉडी, साइज ऑफ द बॉडी, प्रॉपर्टीज ऑफ द बॉडी, एलास्टिसिटी ऑफ द बॉडी, टफ मॉड्यूलस, यंग्स मॉड्यूलस, पोटेंशियल एनर्जी, ये सब न्यूटन ने नहीं बताया, करेक्ट? Action and reaction takes place when they are in contact. Yes, I have seen one. Good. So basically it's not the property of the material. Actually I'll explain you. मान लो कि मैंने मेरा फोन लिया था, okay, I have taken my phone. Now if I just place my phone on my hand and if I keep watching, I'm doing nothing, just I have put my phone on my hand and just watching it like this, will the phone break by itself? I'm not doing anything, I'm just putting the phone on my hand and just watching. Will the phone break by itself? Will the phone break by itself? No, correct? To break this I need some force, okay? So what Newton actually tells is, look, when two bodies are in contact, let's say this is wall and this is maybe something like ball, okay? So when they make contact with each other, if this ball is exerting a force F by ball on wall, okay, then there is an equal and opposite reaction force by wall on ball. Newton just told this, okay? When they try to maintain contact, okay, at that point of contact only Newton's third law is valid, not the traveling of the ball front and back, okay? When these two objects are in contact with each other, then in such case there is equal and opposite reaction force, and this law is actually force has an equal and opposite reaction force. Now once this force is exerted on this ball, now observe carefully, there is a ball like this and there is a force which is applied. Now ultimately, should we really need to learn RTD derivation? No need, but to apply things you should know correctly, okay? So let's see. Now when this is ball and there is some force acting on it, ultimately you know F is equal to ma, and obviously this force will impact this, okay? Now after taking this force F, when they are in contact, ultimately wall भी बॉल पे ऊपर फोर्स एक्सर्ट करते हैं, लेकिन फोर्स लेने के बाद इस ऑब्जेक्ट को क्या होगा? That is not discussed by Newton. Understood? Newton just told you if one object is exerting force on the other, then the other object will also exert the same and exactly opposite equal amount of reaction force on the first object. Okay, but Newton did not talk about this material. Restitution is something different, of course. Okay, but did you all understand this Newton's third law of motion? That's why when you throw a phone onto the wall, after making impact, see, till the phone makes impact, it do not break. Okay, but just at the point of impact and immediately after impact, the wall also exert the force on this phone, and after taking that force, because to break a phone you need some force, that force is actually provided by the wall actually here. Okay, so Newton's third law of motion is valid only when these two bodies are in contact with each other. It's not the going of the ball and coming back of the ball, nothing. Okay, the behavior of the object has nothing to do with Newton's third law of motion. Got it? ये सबको समझ में आया या नहीं? बताओ, ठीक है? Now let's try to understand. Clear? Did you all understand? So when these two are in contact, only at that instant this action reaction pair is present, otherwise no. Okay, then let's see, इसलिए phone वापस नहीं आएगा पक्का. Okay, then second, now let's come back to the classic example what you have told. There is a plate, let's say there is a jet. There is a jet, it's a fixed plate. Okay, it's a jet. So jet का diameter दिया है, मान लो कि capital D at steady state. Okay, then if you talk something, I'm asking you simple question, this diameter is D, or let's say cross section area. So cross sectional area is ये actually here. Okay, so cross sectional area is ये. सर कितने नंबर का आता है इस सब्जेक्ट से? नॉर्मली गेट में सिर्फ 1-2 क्वेश्चंस आते हैं, 2 to 3 मार्क्स, और टू बी फ्रैंक लास्ट 2 साल में एक क्वेश्चन भी नहीं आया, सो इस बार प्रोबेबिलिटी ज्यादा है कि क्वेश्चन आएगा. ओके, ईएससी में टर्बो मशीन्स का लगभग इन प्रीलिम्स एग्जाम, ओके, इन प्रीलिम्स आउट ऑफ 150 क्वेश्चंस, नॉर्मली देयर आर लाइक some 8 to 9 questions, some 10 questions can come on this turbo machines actually. Okay, so ESC में बहुत ज़्यादा वेटेज है. ठीक है, so if I ask this, so मान लो कि मैंने कोऑर्डिनेट सिस्टम सेटअप किया था x y, then force exerted by jet on plate, ये कितना होगा बताइए? This is rho, density of the fluid is rho, cross sectional area of the jet is A, and let's say this is going with velocity v. Then what is the force acting on this plate? MROF minus MRIF. ठीक है, normally whatever the answer finally you want to say, you can say. MA rho a v square, correct? That's what you want to say. Okay, so this is rho a v square, which many of you might have done in this class, fluid mechanics class. So rho a v square, बढ़िया है. Now if rho a v square is the force, then point number 1, this plate, because some force is being exerted, normally मान लो कि अगर आपने F is equal to mass into acceleration बताया, okay, so when this force is exerted on the plate, मान लो कि mass of the plate, then this force is rho a v square, whatever you are telling. Mass of the plate is non-zero, clearly this is not equal to 0, ये भी 0 नहीं है. So इस इक्वेशन से एक्सेलरेशन 0 होना या नहीं बताओ जल्दी, एक्सेलरेशन 0 होना या नहीं? नॉर्मली सिर्फ इस इक्वेशन को देख के बताओ. F इज इक्वल टू एम, ये लेफ्ट हैंड साइड 0 नहीं है, राइट हैंड साइड में एक टर्म 0 नहीं है, सो एक्सेलरेशन 0 होना चाहिए या नो? नो, ठीक है, बढ़िया. सो एक्सेलरेशन शुड नॉट बी 0. अब मान लो कि एक्सेलरेशन 0 नहीं है, तो प्लेट यहां करना है या चलो है? acceleration is non-zero. ठीक है, बढ़िया. So if acceleration is non-zero, then plate यहाँ करना है या जाना है? It should be moving, correct? It should be moving, right? Now when it is moving, ठीक है, then why plate moves? पहला क्वेश्चन ये है कि then why plate is stationary? Of course we have fixed it, so it is stationary. Fine. So this is first question. It is fixed. If it is fixed, then there is some force which is exerted, then this is not moving. Okay, it is fixed. Let's say it is fixed. Okay, simple case. The answer is it is fixed. ठीक है. Then when you are trying to calculate this formula rho a v square, many of you, if I'm not wrong, many of you might have done something like fx is equal to rho av into v minus 0, which gave you rho a minus v square. Correct? This is how you would have solved this. Yes or no? Rho av is the mass flow rate into v minus 0 is equal to rho a v square, of course. तो यही किया था ना आपने. Now one more question. Now come back to the discussion. आपके पास एक वॉल्यूम है लेकिन इसका मास 0 है. ओके, सिर्फ वॉल्यूम है आपके पास. Then when you apply force on this volume, okay, so when you apply some force on this volume, timeline is not showing. What is the timeline? Just a second. It's showing, no, just if you move. Fine. Okay, so when this is volume and this is F, and you are telling in this particular region when this plate is not moving, then if you take this volume in front of this plate, okay, इसको हम बोलते हैं कि कंट्रोल वॉल्यूम. Control volume. Then this control volume is always attached to this plate. Okay, slide map I have tried one, but there is some issue. I think it was not coming up actually. Okay, we'll see along this class. When I ask you questions, I'll on it. Okay, no issue. So let's see. Change in momentum of control volume is action and force exerted by the plate is reaction. Fantastic. Yeah, correct. So let's see. So this is control volume. This control volume is always attached to this plate. Good. But this plate is fixed. It's not moving. So as per this answer, acceleration is 0. If acceleration is 0, F net, of course, this F net should also be 0 actually. Okay, means in this control volume, whatever happens, force acting on this control volume is nothing but force acting on this plate, of course. Okay, because they move. And if you observe Reynolds transport theorem carefully, by Reynolds transport theorem, at steady state, because all the analysis you have done is steady state analysis. So at steady state, dou by dou t of anything is 0. You know this, correct? Normally जब thermodynamics में steady flow energy equation पढ़ाते हैं उस time पे भी dou by dou t of any quantity, whenever you assume steady state, this quantity is equal to 0 actually here, correct? Then this implies dou by dou t of the quantity whatever I have done, integral over v beta times over dv, this is equal to 0. Look, I told you this thing as, I told you this as rate of change of quantity B of control volume. मैंने पढ़ाया था ये, correct? So rate of change of property B of the control volume. Now see how that expression comes up. Dou by dou t is time rate of change. It's okay. Now how this quantity gives you quantity B of control volume, because this word rate of change is basically this derivative, time derivative with respect to any time gives you rate of change. Now how this quantity tells you quantity B of the control volume, beta is intensive property per unit mass. Okay, so beta is basically B by M per unit mass, basis. Okay, this is per unit mass. Now try to understand something carefully. beta is per unit mass. Now, if I take a control volume, this is a volume, of course. In this, if I take a small volume here, okay, if I take a small volume, this volume has dV. Of course, this space is of volume dV. Okay, small elemental volume dV, and very small, almost tending to 0. Then in this space, the density of the mass which is present is O. It is not mandatory that यहाँ density और यहाँ इस दोनों जगह पे density same होना चाहिए. It need not be. Okay, but let's say at this point the density is rho. Then इस छोटा सेक्शन का मास कितना होगा बताइए. इस जो स्मॉल स्पेस है उस स्पेस में डेंसिटी ऑफ द मटेरियल रो है और इसका वॉल्यूम dv. सो इस स्मॉल स्पेस का मास कितना होगा? व्हाट इज द अमाउंट ऑफ मास दैट इज प्रेजेंट इन दैट स्मॉल स्पेस? rho into dv, correct? So therefore dm is equal to rho into dv. Badhiya, good. Okay, rho into dv. Now let's see, if this is dm, then what is the value of quantity b in this small region, in this small space? If mass is dm, the quantity present in the small volume in small volume, the quantity present in the small volume is beta times dm, correct? क्योंकि इस छोटा जगह पे इतना मास है एंड फॉर 1 यूनिट ऑफ मास इस प्रॉपर्टी का वैल्यू बीटा है. सो टोटल क्वांटिटी प्रेजेंट इन दिस स्मॉल वॉल्यूम इज बीटा इंटू dm एक्चुअली. ओके, एंड dm क्या होगा? बीटा टाइम्स रो dv. So this is the value of the property B in this small elemental region actually. Okay, now इस छोटा जगह पे इतना प्रॉपर्टी है, so पूरा वॉल्यूम पे कितना होगा? So therefore total property B of control volume. So मेरे पास इस छोटा जगह का है बीटा टाइम्स रो dv. ना मान लो कि मुझे पूरा स्पेस का प्रॉपर्टी वैल्यू चाहिए, तो इसको क्या करना पड़ेगा बताओ जल्दी. इस छोटा स्पेस का वैल्यू इतना है, बीटा टाइम्स रो dv. अब इस पूरा वॉल्यूम का प्रॉपर्टी पता चलना है तो हम इंटीग्रेट करना पड़ेगा, करेक्ट? लेकिन इस इंटीग्रेशन इस v के साथ करना पड़ेगा, करेक्ट? मान लो कि डेंसिटी, आई एम टेकिंग दिस अजम्पशन लाइक फ्लूइड इज होमोजेनियस, जो जगह है सारी जगह पे फ्लूइड का डेंसिटी हो रही है. ओके, सो इफ आई टेक दिस एंड इफ दिस b इज यूनिफॉर्मली डिस्ट्रीब्यूटेड, ओके, सो बीटा इज इक्वल टू कैपिटल B by m. सो इसको हम इंटीग्रेट करना पड़ेगा, लेकिन ये वॉल्यूम इंटीग्रल होगा, करेक्ट? दैट्स व्हाई दिस क्वांटिटी टेल्स यू the total value of property B of the control volume, which is this. Okay, and dou by dou t gives you time rate of change of that property actually. But जब सिस्टम स्टडी स्टेट में होता है उस टाइम पे इसका वैल्यू 0 होगा. ओके, वॉल्यूम इंटीग्रेशन 3D Stokes theorem. Stokes theorem is something different, not exactly volume integration, but did you all understand this? Yes or no? Please type it in the chat box. Because it's a volume integral. It's a volume integral. Okay, that's why I'm putting a volume integral sign. Got it? And when it is steady state, when this control volume is at steady state, then ultimately rate of change of property of that control volume with the time is 0. That's why this term is 0. Got it? Yes or no? What is beta here? Beta is the property of this property value of beta capital B per unit mass. So थोड़ा नोट करने के लिए 2 or 3 minutes. Yeah, please write it. It's okay. I understand. Like मान लो कि capital B momentum है. Okay, so momentum per unit mass is velocity. Okay, so beta velocity होगा तब बस. मान लो कि B capital B angular momentum है, ठीक है? So उस टाइम पे beta V cos R होगा. Okay, मान लो कि capital B is mass of the system itself. Beta 1 होगा बस. Okay, बिकॉज इट्स अ वॉल्यूम इंटीग्रल ना, सो दैट्स वाई मैंने 3 टाइम्स डिफरेंशिएट किया था. इट्स अ वॉल्यूम इंटीग्रल. देखिए यहाँ डी वी क्या है, वॉल्यूम, स्मॉल एलिमेंटल वॉल्यूम. सो इसलिए हमको पूरा वॉल्यूम पे प्रॉपर्टी का वैल्यू कैलकुलेट करना है तो वॉल्यूम इंटीग्रल लगाना पड़ेगा. ठीक है. फाइन. नाउ लेट्स सी. इफ I want to tell you one thing interesting. If capital B is mass is also extensive property. आप सबको पता है कि mass extensive या intensive? Extensive है ना, क्योंकि depends upon the extent of the system you take, basically size of the system what you take. So if B is mass, beta कितना होगा? B by M, which is equal to mass by mass. So beta कितना होगा? 1, correct? So beta is 1 actually here. Until I ask questions, there is no point of slide map. Okay, I'll on it. Okay, just let's see basically the batch and all, but meanwhile please try to follow the class. Okay, so capital B is mass, then beta is equal to 1. Now I want to tell you one thing. I have a volume. In this there is some particles, of course there is some fluid particles like this. Okay, so if there is some fluid particles, it has some mass m. And this is my system. System is always identified by set of particles. Okay, so system is basically control mass, so is identified by set of particles. Fixed set of particles. Fixed set of particles. Now अब देखिए, मान लो कि मैंने रेनॉल्ड्स ट्रांसपोर्ट थ्योरम का इक्वेशन लिखा था. dB by dt ऑफ सिस्टम इज इक्वल टू वेट ऑफ चेंज ऑफ प्रॉपर्टी ऑफ द कंट्रोल वॉल्यूम प्लस इंटीग्रल. दिस इज द कंट्रोल सरफेस. ओके, सो दिस सरफेस बाउंडिंग द वॉल्यूम इज द कंट्रोल सरफेस. ये होगा कंट्रोल सरफेस. यस, ds or dA, anything. Now observe one thing. At steady state, okay, so at steady state this term is 0 as I have told you. Okay, normally ये जो होता है ये स्केलर होता है क्योंकि प्रॉपर्टी स्केलर होगा. So this is a scalar, or it can be vector also depending whatever the properties you take, but this rate of change is 0 actually. ठीक है. Now if capital B is mass, dm by dt of the system. Okay, for the time being don't take steady state. I'll tell you, I'll make the approximation later. Let's analyze this. Okay, so generally इसका effect क्या होगा देखेंगे हम. अब देखिए, then when capital B is mass, this implies dm by dt of the system is equal to dou by dou t triple integral over the volume V. Beta is 1 rho dV plus double integral over the control surface S. Beta इसका value 1 है, so rho V bar times n cap ds. Okay, or let's put V for the time being. Okay, it's actually relative velocity, लेकिन normally for the time being V ले लो. ठीक है. Now when अगर मान लो कि सिस्टम इज कंपोज्ड ऑफ सेट ऑफ पार्टिकल्स. ओके, सो सिस्टम इज कंपोज्ड ऑफ सेट ऑफ पार्टिकल्स. नाउ व्हेनेवर व्हाटएवर द टाइम यू टेक, सिस्टम डेफिनेशन विल नॉट चेंज. मतलब मैंने जो पार्टिकल्स को मैंने सिस्टम कहा था वो पार्टिकल्स नहीं बदलेगा. ठीक है. सो मान लो कि अगर पार्टिकल्स नहीं बदलते हैं, व्हाट हैपेंस टू मास ऑफ द सिस्टम विथ टाइम? विल इट चेंज और इट वोंट चेंज? प्लीज टाइप इन द चैट बॉक्स. इफ system is identified by set of particles and I am not changing my system all over the analysis, then mass of the system will change with time or will not change with time? It won't change, correct? So mass of the system will not change with time. So if mass of the system will not change with time, इस expression 0 होगा पक्का, correct? System is defined by set of particles, and if let's say for example if I take 5 particles and call that 5 particles as system. Now wherever these 5 particles keep moving, the mass of the system do not change, correct, with time. So ultimately this value is 0. Now do you all, somebody was telling some time back, have you all studied this Gauss divergence theorem? मैथ्स में, वेक्टर कैलकुलस में मैथ्स हुआ या नहीं? पुनीत सर ने कहा था ना, आई मीन ऑलरेडी पुनीत सर ने पढ़ाया मैथ्स. ओके, सो गॉस डाइवर्जेंस थ्योरम. सो गॉस डाइवर्जेंस थ्योरम क्या होता है? मान लो कि आपके पास एक वॉल्यूम है, इसका बाउंडेड एक कंट्रोल सरफेस भी होता है, तो सरफेस भी होता है यहां. सो अब मान लो कि एक फोर्स एफ बार, सम वेक्टर एफ इज एक्टिंग हियर ऑन दिस स्मॉल एलिमेंटल एरिया, एंड ये होगा आपकी आउटवर्ड नॉर्मल वेक्टर एन कैप. ओके, देन दिस गॉस डाइवर्जेंस थ्योरम टेल्स यू integral over the closed surface S f bar dot n cap ds is equal to integral over the volume V divergence of f dv. या देखा सबने? इस गॉस डाइवर्जेंस थ्योरम को देखा आप सभी ने? जब वेक्टर कैलकुलस में आता है, मैकेनिकल के सिलेबस में बहुत इंपॉर्टेंट है. बहुत सारे बार एटलीस्ट वंस इन 2 years क्वेश्चंस कम्स फ्रॉम गॉस डाइवर्जेंस थ्योरम. लास्ट ईयर भी आया था, उस 2023 में भी आया था. सो दिस इज व्हाट गॉस डाइवर्जेंस थ्योरम टेल्स यू, करेक्ट? f डॉट n cap ds is equal to triple integral over the volume v divergence of f dv. yes. now जब मैं कंट्रोल वॉल्यूम बोल रहे, इसका मतलब यह है कि दिस वॉल्यूम, फॉर हैविंग सम फाइनाइट वॉल्यूम, surface has to be closed. okay, so मान लो कि अगर surface closed है, so this is actually closed surface of course because this volume is under this closed surface. So to modify this term I am using Gauss divergence theorem. okay, so by Gauss divergence theorem 0 is equal to dou by dou t of rho dv plus, now this if you appear as per this rho v bar is the vector. okay, rho v dot n cap ds. so I can write this as over the volume v divergence of rho v dv. correct? yes or no? मान लो कि आपके पास एक closed surface है, then this is this part only, I am taking this part. This part is same as this. so if you apply Gauss divergence theorem, this term can be written as divergence of rho v bar dv. correct? can I write this? see, this is Reynolds transport theorem. मैंने बीटा को 1 डाला था यहाँ, तो 1 step and second step. okay, it can be written as, so मान लो कि आपने सिंगल वेरिएबल इंटीग्रेशन करवाए. if you have minus or 2 to 3 x square dx plus 2 to 3 e power x dx, इसको हम क्या लिखते हैं? क्योंकि लिमिट्स ऑफ इंटीग्रेशन आर सेम, वेरिएबल्स आर सेम, कैन आई राइट दिस एज एक्स स्क्वायर प्लस ई पावर एक्स डीएक्स नॉर्मली? ऐसे लिख सकते हैं क्या? ऐसा हो, बताओ जल्दी. वी आर टॉकिंग फ्लूइड मैकेनिक्स. ओके, बेसिक्स ऑफ रेनॉल्ड्स ट्रांसपोर्ट थ्योरम, बेसिक्स, अल्ट्रा बेसिक्स. ओके, नाउ ये दोनों टर्म्स का इंटीग्रेशन सेम वॉल्यूम पे है. ठीक है, सो आई कैन राइट दिस एज, और यहां एक और चीज, you can change this integration and differentiation. okay, because this is with respect to time and this density can change with respect to time. so basically you can interchange this differentiation and integration, doesn't matter. okay, so 0 is equal to integral over v dou by dou t of rho plus divergence of rho v dv. ऐसे लिख सकते हैं क्या? yes or no? please type in the chat box. can I write these two integrals because they are under same volume? so I can write it as simple one under one integration, same logic. can I do this? yeah, if I can do this, then dv is arbitrary choice. मतलब मान लो कि मैंने dv को यहां सेलेक्ट किया और यहां किसी भी जगह पे क्या सेलेक्ट किया, तो ये इंटीग्रेशन इतना ही आएगा. ओके, इसका मतलब ये है कि मान लो कि मैंने एक चीज क्लैरिफाई करता हूं, मान लो कि इस ए और बी के इरेस्पेक्टिव इस इंटीग्रेशन ऑलवेज 0 आ रही, ओके, किसी भी वैल्यूज डाल दो ए और बी की जगह पे, दिस इंटीग्रेशन इज ऑलवेज गिविंग यू 0, देन दिस टेल्स यू दिस एफ ऑफ एक्स इज 0 एक्चुअली। वह एक ही पॉसिबिलिटी है कि जब इस लिमिट्स के बेसिकली इट डजंट डिपेंड ऑन दिस लिमिट्स, बट दिस इंटीग्रेशन ऑलवेज पक्का 0 आएगा, ओके। सो दिस टेल्स यू जो इंटीग्रेंड है यहां ये 0 है पक्का। ये क्या है? किसी ने देखा था इसी इक्वेशन को? ये तो कंटिन्यूटी इक्वेशन आ गई, बस कंटिन्यूटी इक्वेशन, करेक्ट ना? इट इज कंटिन्यूटी इक्वेशन, ठीक है। नाउ कंटिन्यूटी इक्वेशन है ना, बढ़िया। डोंट वरी, सी आई नो दैट मेनी ऑफ यू माइट नॉट हैव स्टडीड रेनॉल्ड्स ट्रांसपोर्ट थ्योरम, मुझे दिमाग में आ गया, सो इसलिए मैंने पूरा रेनॉल्ड्स ट्रांसपोर्ट थ्योरम में 3 टर्म्स है, एक dB by dt ऑफ द सिस्टम, दूसरा वो डो बाई डो टी वाला, थर्ड वो डबल इंटीग्रल ऑफ द सरफेस, ओके। सो डो बाई डो टी ऑफ ट्रिपल इंटीग्रल मैंने आपको पढ़ाया, ओके, थोड़ा सा डिटेल में, एक स्मॉल वॉल्यूम dV लेके इस चीज मैंने आपको पढ़ाया था, कहाँ? या, ओके। सो दिस सिमिलरली मैं जो तीसरा फॉर्म होता है, मतलब तीसरा टर्म है इस डबल इंटीग्रल वाला, उसको भी मैं आपको दिए से समझता हूं, ठीक है। सो बट दिस टेल्स यू दिस इज कंटिन्यूटी इक्वेशन। एक ब्यूटी ये है कि in this volume I did not take this divergence out as constant, okay, so here density is not constant, still it's not a compressible flow, okay। मान लो कि अगर इस टाइम पे मैंने स्टडी स्टेट का assumption लिया, तो if I take steady state assumption this first term will be 0, which tells you only this term is 0, still you have derivative inside, okay, I mean sorry, this density inside, clear? So ये है continuity equation, this is continuity equation, continuity equation, fine. Our LHS is 0 because system is defined by a set of particles and these particles will not change with time, so mass of the system always remains constant, that's it, okay. Momentum can change depending on the forces that are acting on it, but mass of the particles will never change, that's why, okay. So this is this equation. Normally, have ever seen this equation? इस इक्वेशन देखा किसी ने? del square t plus q dot gen by k is equal to 1 by alpha blah 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 whatever, देखा किसी ने इस इक्वेशन को? यस, ये इक्वेशन क्या है? नो नो नो, हीट कंडक्शन इक्वेशन। अच्छा, इसको नहीं देखा, अब लोगों को बताया कि इसको देखा। okay, yes, conduction equation, the same conduction equation can also be derived from Reynolds transport theorem again, okay, yes, you can again use the same, we didn't study heat conduction yet, acha, heat transfer didn't start it, okay, fine, but normally this is heat conduction equation. You can also show the same equation within 3 steps, just 3 to maximum 4 steps for your understanding. I can prove this equation using the same logic. Like normally इस इक्वेशन को लाने के लिए बहुत कोशिश करते हैं आप लोग, करेक्ट? एक छोटा सा वॉल्यूम लेते हैं, सो मास गोइंग फ्रॉम दिस साइड, मास लीविंग फ्रॉम दैट साइड, मास कमिंग इन फ्रॉम अप, मास कमिंग आउट फ्रॉम डाउन, सो यू विल टेक ऑल द 6 faces of the cube, do big mathematical calculations, substitutions, after doing everything you will get this equation, right? लेकिन यहाँ देखिए सिर्फ 3-4 steps में आया था। So are derivations necessary? बहुत बढ़िया क्वेश्चन है। मैं एक ही चीज आपको बताता हूँ गाइस, मान लो कि, क्योंकि आपको पता है मैंने BRC में काम किया था, HPCL, ओके, ये सारी जगह पे है, अगर मान लो कि आपकी टारगेट सिर्फ गेट लिखना और गेट में मार्क्स लाना है तो इतना भी नहीं पढ़ना सकते. यू नीड नॉट इवन डू दिस मच. ओके, जस्ट सम वेरी बेसिक डेफिनेशंस कुड मेक यू क्वालिफाई गेट एग्जाम. ओके, गेट क्वालिफाई होना बहुत आसान है एक्चुअली. ठीक है, लेकिन जब गेट में सिलेक्शन मतलब मार्क्स आते हैं, इफ यू वांट टू गो टू पीएसयू, ओके, और यानी किसी भी गवर्नमेंट सरकारी नौकरी पे जाना है तो इंटरव्यू होगा पक्का. ओके, उस इंटरव्यू में आपका एनालिटिकल स्किल्स टेस्ट करेगा. क्योंकि आई विल टेल यू वन थिंग. मान लो कि आपको एक सरकारी नौकरी मिला था. ओके, मान लो कि एचपीसीएल में ऑफिसर का पोस्ट मिला था. आई थिंक सम ऑफ यू हैव अप्लाइड. आप क्या एक्सपेक्ट कर सकते हैं आफ्टर गेटिंग पोस्टिंग? Do you expect people ask you, for example, fallen eagle? Okay, so hello fallen eagle, please come here. So write what is first law of thermodynamics. Do you think that they ask you this? नहीं, करेक्ट. आप थोड़ा रिसर्च करना पड़ेगा, आप थोड़ा मैथमेटिकल एनालिसिस करके सिस्टम्स को डिजाइन बिल्ड करना पड़ेगा. ओके, सो इसलिए मैथमेटिकल एनालिसिस कैसे करना है सिस्टम्स को, ये चीज़ आना ज़रूरी है. ओके, दूसरा चीज़ ये है कि मैं बहुत स्टूडेंट्स भी मुझे कंप्लेन किया था एक्चुअली. सर मुझे आईआईटी में मतलब गेट में अच्छा 500 से नीचे रैंक आया था, मैंने आईआईटी में गया था, लेकिन सर यहाँ जो लोग पढ़ाए कुछ भी समझ में नहीं आ रहे क्योंकि मेरा मैथ वीक है, मुझे इंग्लिश समझने में दिक्कत है. सी आई विल टेल यू वन थिंग. ठीक है, ऑफ कोर्स दिस इज एन हिंदी बैच, आई डू एक्सपेक्ट हिंदी बैचेस, इंग्लिश बैचेस, ऑल दिस थिंग्स, बट एक चीज़ इंपॉर्टेंट है कि प्लीज़ ट्राई टू स्टडी थिंग्स इन इंग्लिश, अंडरस्टैंड इन इंग्लिश. ओके, ये लॉन्ग रन में आपको बहुत मेहनत करेगा. ठीक है, कैन एनी वन आस्क कॉन्फिडेंटली सिटिंग इन एन IIT और IISc, सर समझ में नहीं आया, एक बार हिंदी में पढ़ाइए. कैन यू से दिस? कैन एनी वन से दिस? मान लो कि आपकी फैकल्टी आया था, सेम चीज़ उन्होंने पढ़ाया वहाँ IIT मद्रास में या लेकिन IISc में किसी जगह पे. कैन एनी वन टेल सर समझ में नहीं आया, एक बार हिंदी में पढ़ाइए, एक बार कुछ और लैंग्वेज में पढ़ाइए, एक बार भोजपुरी में पढ़ाइए? ऐसा बोल सकते हैं क्या? नहीं ना. सो बात तो पॉइंट वाली बोल रहा है सर. या आई एम टेलिंग यू. ओके, कभी कभी तब सुना पड़ेगा ऑब्वियसली. ओके, दूसरा चीज़ ये है कि मान अगर IITs या लेकिन IISc में आप लोग एमटेक करने का प्लान है तो वहाँ बहुत सारे लोग मतलब लाइक गेस्ट लेक्चरर्स एंड गेस्ट प्रोफेसर्स विल बी फ्रॉम फॉरेन. ओके, सो उस लोगों को मतलब लाइक अंडरस्टैंड करना बहुत मुश्किल होगा. ठीक है, so please make this a habit. They might teach in Bengali in IIT KGP, lol, never. Okay, किसी भी IIT में, किसी भी IISc में, किसी भी IIT में never it happens. Okay, in order to survive in corporate, आप किसी भी जगह पे जाओ, IIT, PSU, corporate, whatever, प्लेसमेंट लेके, मान लो कि 10 करोड़ का प्लेसमेंट लेके कॉलेज किसी कंपनी पे जाना है. ठीक है, then also it will English should not be a barrier. ठीक है, so please do that. My native language is not English and I am not a fan of England people, but just I'm telling this, okay, because ये fact है. ठीक है, 18 को HPCL का एग्जाम है, कोई टिप्स देता हूँ. ओके, जब क्लास चलते हैं तब देता हूँ. नाउ लेट्स कम टू आवर मेन कंसर्न, लीनियर मोमेंटम. मैं एक छोटा सा सिंपल एग्जांपल लेके आपको पढ़ाता हूं ये कंटेंट. ओके, सो इससे पहले एक चीज है कि ये क्या होगा. ये क्या होगा, करेक्ट. तो पहले वाले जाने के बाद हो जाइए, डोंट वरी सर. हाँ, सो आई एम टेलिंग यू. सो इस टर्म भी है हमारा रेनॉल्ड्स ट्रांसपोर्ट थ्योरम में. इस टर्म हमको क्या सोचेगा, लुक आई विल टेल यू. मैंने एक चीज यहां लिखा था, नेट रेट ऑफ एफ्लक्स क्रॉसिंग द कंट्रोल सरफेस. इसका मतलब क्या होगा, लुक आई विल टेल यू. मान लो कि आपके पास एक पाइपलाइन है. ओके, सिंपल चीज, आई एम जस्ट टेकिंग सम सिंपल कंट्रोल वॉल्यूम सो दैट यू ऑल अंडरस्टैंड. सो कैन आई मेक ए कट लाइक दिस. मैंने ऐसा कट करके तब यहां सेक्शन एलिप्स आएगा, पक्का आप सबको पता है कि सेक्शन एलिप्स आएगा अगर मैंने स्लैंटली कट किया तो. मान लो कि इस एलिप्स का एरिया ये, ओके, दिस एरिया ऑफ दिस एलिप्स इज ए. मैंने स्लैंटली कट किया पाइप को. ओके, एंड फ्लो वेलोसिटी इन दिस डायरेक्शन इज v and density is O common because it's a incompressible flow, in anyway it's constant. Then can I write mass is equal to rho a v taking this area and this velocity? can I write m dot is equal to mass crossing this surface is equal to rho a v, such that this a is not straight but slanted and v is actually in this direction. Can I write this or no? Yes, लिख सकते हैं? No? Swati wants to support no so much. Others want to say yes so much. What is a flux? I'll tell you. Just a minute. ठीक है? अब मान लो कि मेरा पाइप है, पाइप का डायमीटर d. So m dot is equal to o into pi by 4 into d square into v. ये सही एक्सप्रेशन है, सबको पता है कि आप लोगों ने बहुत सारे क्वेश्चंस में इस एक्सप्रेशन को यूज किया था. अब बताइए, इफ दिस इज m dot and this is pi by 4 d square, is pi by 4 d square and is shaded area इक्वल होगा या नहीं? इक्वल होगा या नहीं बताओ. इस pi by 4 d square and उस जो शेडेड पार्ट है एलिप्स का, वो दोनों इक्वल होता है या नहीं? नहीं, नॉट इक्वल. करेक्ट. सो जब आप इस फॉर्मूला अप्लाई कर सकते हैं, इसमें एक रिस्ट्रिक्शन ये है कि इस एरिया और ये वेलोसिटी दोनों परपेंडिकुलर होना चाहिए. ठीक है. सो रो ये वी व्हेन यू आर यूजिंग दिस एक्सप्रेशन, ये शुड बी ऑलवेज परपेंडिकुलर टू वी ऑफ कोर्स. गॉट इट? फ्लो एरिया होना चाहिए. इट्स नॉट लाइक द फ्लो एरिया बट द क्रॉस सेक्शन एरिया टू द flow. If this is the flow's direction, then the perpendicular to this is the cross section, cross perpendicular. So cross section का area लिखना चाहिए. Okay. If area and velocity are not perpendicular, sometimes it happens. Okay. Generally कभी-कभी places पे ऐसे होता है कि area और jet velocity दोनों perpendicular नहीं होते. उस टाइम पे क्या करते हैं? देखिए, if this is the area and if this is the velocity in this direction, okay, then what you'll do, एक small area pick कीजिए dA, okay, and इसका unit normal n cap होगा पक्का. Okay, unit normal is n cap, always denoted with n cap. So in such case, what you do, you resolve this velocity. If this is v, now if this angle is theta, then this would be v cos theta. Correct? This would be v cos theta. Then for this area, this v cos theta velocity component is perpendicular. Then you can write m dot is equal to rho a v cos theta actually here. Where what is theta? Theta is angle between unit normal vector and the velocity. अब मान लो कि okay, so this is v cos theta. Okay, so cos theta is the angle between the velocity and normal to the surface. So theta is angle between velocity and normal to the surface. Normal to the surface. अब मान लो कि यहां द सेम पाइपलाइन, लेकिन सेम फ्लूइड वेलोसिटी v यही है, लेकिन मैंने एरिया ऑफ क्रॉस सेक्शन यही लिया था, बिकॉज क्रॉस सेक्शन इज ऑलवेज परपेंडिकुलर. सो this is the area what I have taken. Means basically in the side view you can see there is a circle which comes up. Okay, so this is a circle. Then if this is the surface, the outward normal to this surface would be in this direction. Okay, so this is n cap. Clear? So flow is going here, so this is the surface. The outward normal, see basically in this case, if this area gets straight, this angle or this n cap will also get exactly, see both are like this. When they are like this, now if you make them straight, this n cap will become horizontal. If n cap becomes horizontal, what is the angle between v and n? Ab batao, what is the angle between this v and n in this case? If you take a cross section area 0, correct? So अब यहां 0 डालने पे cos 0 कितना बताओ? cos 0 का वैल्यू कितना आएगा? cos 0 का वैल्यू कितना आएगा? वन. ओके, जब तक वेलोसिटी एंड एरिया दोनों परपेंडिकुलर नहीं है, यू कैन नॉट अप्लाई दिस डायरेक्टली. ठीक है, and this is OAV cos theta where theta is this. Now in this expression observe something, n cap is unit vector, outward normal unit vector, outward unit normal. ओके, इसका मतलब मैग्नीट्यूड ऑफ n cap कितना होगा? कैन एनीवन प्लीज टाइप इन द चैट बॉक्स? n cap is the unit outward normal, so magnitude of n cap कितना होगा? It's unit vector 1. Can I say correct? Yes or no? Dot product a dot b is equal to mod a into mod b into cos theta. पता है, 11 कक्षा में पढ़ाया, लेकिन डिप्लोमा फर्स्ट ईयर में भी पढ़ा. Now let's see magnitude of velocity. Just I'm writing it as v cos theta because v into 1 into cos theta is v cos theta. I can write this as v dot n actually here. Okay, v dot n, which tells you that if you take any surface, the amount of mass which is cutting that surface and going is given by m dot is equal to, if you observe this normally, rho a v cos theta can be written as v dot n cap, where this n cap is unit normal to this area. That's it. So this is, what is n cap? Unit normal vector. Okay, if this is the surface, the outward unit normal actually to this area. Clear? So that's why flow rate is always given by this expression, and this is a special case when a and b are perpendicular to each other, because when a and b are perpendicular to each other, the normal to a and b will be parallel to each other. Got it? ये चीज सबको समझ में आया या नहीं, बताओ? ओके, ये सब चीज मैंने सिर्फ हंगामा के लिए नहीं पढ़ा रहा हूं. जब वेन्स डिस्कस करते हैं ना, when vein angle is theta, jet angle is alpha, you will have confusions. That's why I'm teaching all these things. So please listen carefully. Okay? Fine. So see here. Is this clear? Then let's see. Now this tells you, if you take the same control volume, if you take this as some small elemental area ds, okay, इसका n cap होगा ऐसे, and maybe let's say velocity, the fluid is coming in this direction. It can have multiple ports. Okay, so at some locations fluid can come, at some locations fluid can go in. All these things can happen. Okay, normally, because in a control volume generally it can have a lot of connections, obviously. Okay, then if you focus on this small area, small ds, and beta is the property per unit mass, the rate of, or the property, the quantity b that leaves the control surface, Can I write this as beta times mass flow rate leaving the control surface, or mass flow leaving the control surface, or you can say the quantity weight, the weight of quantity that leaves the control surface, mass flow rate leaving the control surface. Can I say this? Yes or no? Yes or no? Please type in the chat box. Can I write beta into the mass flow rate which is leaving the control surface is exactly same as the quantity b leaving the control surface. Correct? Now अब इस छोटा surface को ले लीजिए. Okay, so ds is the small elemental surface area. If ds is the small elemental surface area, क्या मैं यहाँ beta into rho v dot n cap dA or ds, whatever, if the area is ds. So can I write this? Because if ds is the area, mass flow rate leaving that area is rho ds into v dot n. So rho v dot n into ds. Yeah, okay. Yes or no? Please type in the chat box. Did you all understand? Now this is the quantity B which is leaving to this small surface ds. If I want to calculate the property leaving to the total control surface S, okay, if I want to calculate the quantity leaving to the total control surface S, then what I have to do? I have to put integral over the control surface, but this surface is closed in this case, that's why I have this expression. A is there, this ds, O into V dot N into ds. ds is the small elemental surface area here. Okay, got it? O time beta times O V dot N cap ds. Okay, so whatever the property that is changing for the system is equal to rate of change of property of the control volume. Can't we take it as dA? We can take, no issue. If you normally, I am habituated to write this as S. S denotes the surface. So if you are comfortable, you can write with A, no issue. It's just a notation, that's it. Okay, nothing can be done. dA. Okay, happy? Then this is the net rate of quantity which is leaving the control surface, actually, or which is cutting the control surface, actually. Okay, this is the net rate of property which is actually cutting this control surface, actually, here. Okay, now why I'm telling all these things? Look, let's come back to the case of the Newton's second law of motion. When you apply Newton's second law of motion, F net acting is equal to mass into rate of change of momentum. But the body should have some mass, so this is basically on system, actually, on fluid, is equal to net force acting on the fluid. Yeah, ds also right, anything you can use, just a notation. Okay, so F net acting on the fluid, because from Newton's second law of motion, what you know, if a body has some mass, अगर मान लो कि एक body को थोड़ा सा mass है, तब when you exert a force on that body will accelerate. Acceleration is nothing but rate of change, acceleration into mass is nothing but rate of change of momentum. लेकिन इस जो मोमेंटम चेंज होता है ये इस मास का होता है. ओके, और मास वॉल्यूम को नहीं होगा. कंट्रोल वॉल्यूम, नॉर्मली कंट्रोल वॉल्यूम जो होता है इसका नहीं होगा. कंट्रोल वॉल्यूम में जो मास होता है उस मास का दिस m एग्जिस्ट होता है. गॉट इट? नॉर्मली मान लो कि आपने एक टैंक लेके चला था, ओके, वैक्यूम टैंक. देन इनसाइड द वैक्यूम टैंक देयर इज नथिंग, इट्स जीरो, मास इज जीरो, बट देयर इज ओनली स्पेस, सम वॉल्यूम. बट इन दैट स्पेस व्हेन यू फिल सम पार्टिकल्स, देन the system has some mass, actually. Okay, and the forces what you are exerting will act on that fluid. D F net acting on the fluid is nothing but, since my fluid particles are my system, so d by dt of momentum change of the system, actually, here. And in Reynolds transport theorem, if you take capital B to be linear momentum, which is m into v, this part which is on the right hand side is actually the left hand side of the RTT. Got it? Okay, in RTT I'll tell you, look, for B is equal to mv, d by dt of mv of the system, which is net force acting on the fluid, net force acting on the fluid is equal to assume steady state. Okay, we are assuming steady state anyhow, simply. So assuming steady state, this gives you something like integral over the control surface S. Now this tells you beta B by M, which is V, of course. So this is equal to V times, beta is V, of course. So V times, this is V, a vector, times the mass flow rate, which is scalar. So rho V dot n cap dA. This is what you have here, of course. Okay, so rho V dot n cap dA. This is what you get, actually. Now sigma net force acting on the fluid, which is this quantity, is equal to this one, because I have taken steady state, so dou by dou t term is 0. Okay, then observe something, थोड़ा सा ध्यान लीजिए. हाँ, this is the last step. Okay, if you understand this, all the impact of jets is understood. So see here carefully, V bar times rho V dot n cap dA. Okay, so this is what you have. Now This thing which is here is scalar, correct? क्योंकि ये dot product है, density भी scalar है, so scalar into scalar gives you some scalar. This is vector and dA is a vector, of course, elemental area. Now, when you have a control volume, I just want to tell you two things. Look, when you have a control volume, this integral takes out the interaction at all points on the complete control surface, okay? But I want to tell you one thing. मान लो कि यहाँ एक थोड़ा सा एरिया लिया था आपने ds1, ओके, और यहाँ ds2. तो लेट्स से यहाँ एक इनलेट है v1 और यहाँ एक आउटलेट है v2. लेट्स से, ओके, सो दैट इज v2. देन एट ऑल पॉइंट्स ऑफ इनलेट, जहां जहां आपने इनलेट लिया था उस सारे जगह पे मान लो कि आपने n कैप भी ड्रॉ किया, यूनिट नॉर्मल वेक्टर आउटसाइड, ओके, और यूनिट आउटवर्ड नॉर्मल, यूनिट आउटवर्ड नॉर्मल at all entries of the fluid angle between V and N, is it less than 90 or more than 90? Can you tell me? At all points of inlets, this integral is over the complete control surface. So जहां जहां fluid enter हो है वो सारे points को लेते हैं इस integral. लेकिन मैं ये चीज पूछना चाहता हूं कि जहां जो fluids का entry है उस टाइम पे, if you take, see carefully, maybe the diagram is not very clear. Look, n cap is something like this, velocity is something like this, let's say. तो इन दोनों का एंगल ग्रेटर देन 90 और लेस देन 90? इट इज मोर देन 90 ना. देखिए वेलोसिटी ऐसा है, n कैप ऐसा है, correct? It is greater than 90. This is V and n is something like this, so the angle between those two is greater than 90, correct? So if this is greater than 90, V dot n ये क्या होगा, पॉजिटिव या नेगेटिव? बताओ जल्दी. Yeah, we measure from the tail of the vector obviously. So if angle is greater than 90, ये dot product नेगेटिव होगा या पॉजिटिव होगा? नेगेटिव, correct? So this is negative. बढ़िया. Similarly, at all entries or at all exits, sorry, at all exits of fluid, angle between V and N is, ये greater than 90 होगा या less than 90 होगा? बताओ जल्दी. Greater than 90 होगा या less than 90 होगा? This is less than 90. If this is less than 90, this implies V dot N is positive, correct? क्योंकि यहां देखिए, if this is N, if this is N and if this is V, ultimately the angle between them is less than 90, so it is positive, correct? It's less than 90, so the angle, the V dot product is positive. Can I break this integration into two parts? Therefore, sigma f acting on fluid, sigma f acting on fluid, this, because the rate of change of momentum is of mass, not the volume, okay? So this mass is for this fluid, not the volume. So this is equal to double integral over control surface V dot n cap ds, ds some fans for something, so V times rho V dot n cap dA. This is what you have. Since this integral take care of all points where fluid is crossing the control surface, can I break this integral into two parts such that one consists of summation of all inlets V dot rho V dot n cap dA plus summation of all outlets Can I write it like this? Yes or no? Because this integral takes care of both inlet points, outlet points, wherever the fluid is cutting the control surface, at all those points it's taking care. So I can divide the control the complete all points into two parts. One set of points where all fluid is going inside the control volume, and one set of points where fluid is always going out of the control volume. Yes. So basically the double integral over the control surface tells you the interaction at each and every point where fluid is cutting the control surface. Okay. Now when fluid is cutting the control surface, उस सारे पॉइंट्स को मैंने दो अलग कैटेगरीज में डिवाइड कर रहा हूं, एक पूरा इनलेट्स एंड एक पूरा आउटलेट. सो मान लो कि अगर आपके पास एक वॉल्यूम है लेकिन इसका दो इनलेट्स और एक आउटलेट है, मान लो कि ऐसा, ठीक है. सो टोटल देयर आर 3 पॉइंट्स वेयर दिस फ्लूइड इज कटिंग द सरफेस, बट लेकिन उस तीन पॉइंट्स में दोनों इनलेट्स है, ये आउटलेट है. ओके, सो वी कैन डिवाइड. व्हाई आई एम डिवाइडिंग दिस is at all inlets this is negative. Okay, so this dot product, this is negative at all inlets. At all outlets this is positive. Just now you have told me this is positive. So in the negative inlet would be negative always here in this case, because this v dot n is negative, because whenever fluid is going in, the outward normal and the velocity will make an angle more than 90. Okay, now let's see. So therefore isko hum kya likhte hain? Tell me one thing, this negative sign will bring out, but if you take the magnitude of rho v dot n dA, what does this gives you if you take magnitude of this? ठीक है, नेगेटिव साइन हम इस सबमिशन के बाहर लिखेंगे, लेकिन इसका मैग्नीट्यूड क्या होता? नॉर्मली व्हाट इज इट? ओ वी डॉट एन डी ए इन मैग्नीट्यूड. इफ यू टॉक इन मैग्नीट्यूड, इफ यू टॉक, व्हाट इज दिस ओ वी डॉट एन? ऑलवेज पॉजिटिव. ठीक है, मैग्नीट्यूड पॉजिटिव होता है, लेकिन फिजिकली क्या होता है? अरे वो वी डॉट एन कैप डी क्या होता है? मास फ्लो रेट ना. भूल गया मैंने जो आधा घंटे से पहले क्या भव भव कर रहे, वो सब भूल गया लोग ने. हाँ, इसको इफ दिस यू टेक मॉड्यूलस, दिस इज ऑलवेज पॉजिटिव, विच टेल्स यू द मास फ्लो रेट. करेक्ट, फ्लो रेट, मास फ्लो रेट. सो देयरफॉर इस नेगेटिव साइन को हम बाहर लिखेंगे. सिग्मा एफ on fluid, net force acting on fluid, is equal to this minus sign, if you write minus, this can be written as summation m dot velocity at inlet plus summation at the outs. This is in. Okay, anyhow I have written inlet here, so m dot in v in, m dot in v in plus summation m dot out outlet, actually here. Yes, can you all observe this? So therefore, is this clear or not to all of you? Net force acting on the fluid is given by, okay, if you write plus sign here, then it is outlets, because some of you are happy to write this again. Then is my plus sign ko minus laga ke, this is inlets, maybe that you can do. Yes or no? I won hearts for this derivation, thank you. बहुत सारी चीज़ है हमारे पास ऐसे, ठीक है, लेकिन to be frank I'll teach only up to gate level. Okay, no issue, fine. अगर आप लोगों का हीट ट्रांसफर भी हुआ तो मैंने वो कंडक्शन इक्वेशन है ना, जनरल कंडक्शन इक्वेशन, बहुत मेहनत करके डेराइव करते हैं उस चीज़ों को, लेकिन यही गॉस डाइवर्जेंस थ्योरम लगा के 3-4 स्टेप्स में करके दिखाता हूँ, ठीक है, लेकिन बाद में करता हूँ. फाइन. नाउ वन इंपॉर्टेंट पॉइंट इज, I'll ask you something. Now let's come back to the first point what I was talking in this class. Second slide or first slide, I don't remember. हाँ, ये वाला. इस आंसर कैसे आया अब हम देखेंगे थोड़ा सा डिटेल वे में, ठीक है. कब तक क्लास होगी? टुडे आई एम प्लानिंग टू कीप इट शॉर्ट, मे बी 9:30 9:40 समथिंग लाइक दैट. ओके, बिकॉज पहला दिन है ना, अब तक लोड ज़्यादा हुआ ऑलरेडी, ये वेक्टर कंट्रोल वॉल्यूम इंटीग्रल, करेक्ट। बहुत लोग ने ऐसा किया था ना, जब लेक्चर देखा क्या बोल रहा है इस बंदे ने, शिवम साहब आसान से पढ़ रहे, ये बंदे आया सडनली, पता नहीं कि ये बंदे है आज तक, सडनली आया, ये बोला कि वेक्टर है, इंटीग्रल है, डबल इंटीग्रल है, ट्रिपल इंटीग्रल है। ज़्यादा लोड नहीं लेना आज। करेक्ट, इट्स ओके, नो इश्यू। लेकिन भाई मैं एक चीज़ आपको, थोड़ा सा इंपॉर्टेंट चीज़, गॉट माई फीलिंग्स, मुझे पता है अंकित, ठीक है, क्योंकि जब मैंने पहला बार 2017 पे आईआईटी मद्रास में बैठा था, बीटेक के तुरंत मुझे एडमिशन मिला एक्चुअली, ओके। सो मैंने बैठा था एक्चुअली, देन देयर इज ए वेरी फेमस गाय हु डिड हिज पीएचडी फ्रॉम आईआईएससी बैंगलोर विद इन 2 years, उनका नाम है शामिद बख्शी सर। सो आईआईटी मद्रास में, सो वो आया था क्लास में। At least now I am giving you these explanations, okay, I am giving you these explanations, like why this volume integral, why double integral, why v dot n cap, I have told all these points till now. उस दिन जब मैंने क्लास में बैठा था कुछ explanation नहीं है, this is all fun stuff, basic stuff you might have seen, so this is what it does, this done, okay. So I am telling you, unless your maths is very good, तो आपकी हिंदी वीक है ना, वीक नहीं, बहुत अजीब है, ओके, टू बी फ्रैंक। आई वाज रिसेंटली स्टार्टेड वाचिंग हिंदी मूवीज टू पिक अप माई हिंदी, ओके, एंड चेन्नई एक्सप्रेस मेरा फेवरेट भी है, ठीक है, फाइन। चलो अब हम देखेंगे कि इस आंसर कैसे आएगा। लुक, दीज वेलोसिटीज आर द वेलोसिटीज एट विच दिस फ्लूइड इज कटिंग द कंट्रोल सरफेस, है ना, क्योंकि जब हमने इस एक्सप्रेशन लिखा था, इस v, दिस इज द मास विच इज कटिंग द कंट्रोल सरफेस, मतलब इस वेलोसिटी ये है कि जो वेलोसिटी से फ्लूइड कंट्रोल वॉल्यूम पे एंटर या एग्जिट हो है, ओके, सो वो वेलोसिटीज है। लेकिन इन जनरल दीज आर रिलेटिव वेलोसिटीज, क्योंकि मैंने कंट्रोल वॉल्यूम को फिक्स करके ये सारा डेराइव किया था, क्योंकि आप लोग बहुत इंटेंस हुआ अभी तक, सो इसलिए मैंने कंट्रोल वॉल्यूम को फिक्स करके डेराइव किया था ये सब। बट इन जनरल नॉट ऑल आईआईटीज आर लाइक दिस, so you're learning fast, maybe better, okay. So let's see, normally जब कंट्रोल वॉल्यूम भी मूव करते हैं, okay, because I have taken the plate to be fixed actually, okay, मान लो कि अगर प्लेट मूव है, लेकिन नॉर्मली जब जेट टर्बो मशीन पे इंपैक्ट हुआ है वेन पे, सो उस टाइम पे जब व्हील रोटेट होते हैं ना, सो वेन का मूवमेंट भी होगा, ओके, सो वेन हैज अ वेलोसिटी इन सच केस, सो उस टाइम पे यहाँ रिलेटिव वेलोसिटी डालना पड़ेगा, ठीक है। सो लेट्स ऑब्जर्व वन थिंग केयरफुली। अब जाएंगे इस क्वेश्चन पे, ठीक है, तो okay, fluid is going with a velocity v, then if there is no friction and nothing, there is no friction on the blade anything, the fluid just slightly smoothly slides with velocity v, of course, correct. This is what it ideally happens. If there is no friction at these edges, then no energy is lost, this fluid will just go and come out. Everywhere pressure is open to atmosphere, so there is no pressure difference anywhere. Now let's see, can I ask you something? आपने यहां एक कंट्रोल वॉल्यूम लिया, ठीक है, बिकॉज मैंने इसी वॉल्यूम को क्यों लिया, दिस इज द वॉल्यूम और द रीजियन इन विच फ्लूइड एंड प्लेट आर कमिंग इन कॉन्टैक्ट विथ ईच अदर, ऐसा हो नो। सो आपने पूछता कि सर व्हाई डोंट वी टेक वॉल्यूम हियर और हियर समवेयर, लेकिन जो वॉल्यूम पे फ्लूइड और बॉडीज इंटरैक्ट हो रहे वो वॉल्यूम हमको इंपॉर्टेंट है, ठीक है। सो इसलिए इस वॉल्यूम मैंने लिया था, एंड दिस इज माय कंट्रोल वॉल्यूम, कंट्रोल वॉल्यूम। सो मैंने मैं कंट्रोल वॉल्यूम को फिक्स किया था क्योंकि प्लेट भी फिक्स्ड है, सो प्लेट के अकॉर्डिंग कंट्रोल वॉल्यूम भी फिक्स्ड है। लेकिन इस कंट्रोल वॉल्यूम में जो फ्लूइड है वो फिक्स्ड नहीं है, क्योंकि मान लो कि एट टाइम t इक्वल टू 5 seconds some fluid particles enter this volume, at t equal to 15 seconds these particles may not be in this volume, correct, क्योंकि फ्लो की वजह से बाहर जाते हैं, or maybe if vein is very big then it may, these particles might be here somewhere, okay. सो लेट्स ऑब्जर्व समथिंग. अब न्यूटन थर्ड लॉ लगेंगे हम, क्योंकि इस वॉल्यूम पे फ्लूइड एंड प्लेट आर इन कॉन्टैक्ट विथ ईच अदर. ओके, बिकॉज सी टू बी फ्रैंक आई हैव डन दिस, बट इस लाइन एक्चुअली प्लेट से अटैच्ड है. ओके, यू ऑल नो, लाइक कंट्रोल वॉल्यूम हैज बेसिकली नो थिकनेस, सो अल्टीमेटली दिस आर एक्चुअली सेम. सो लेट्स सी. सो आज सब्जेक्ट कब खत्म होगा, ये सब्जेक्ट कब खत्म होगा. द प्लानर फॉर दिस वाज एक्चुअली गिवन, इट वाज स्लाइटली डिस्ट्रीब्यूटेड. देखेंगे, ठीक है. सो लेट्स सी. फ्रॉम न्यूटन्स थर्ड लॉ, फ्रॉम न्यूटन्स थर्ड लॉ, in this control volume, force acting on plate by fluid yes or no? Correct? प्लीज टाइप इन द चैट बॉक्स. क्योंकि उस कंट्रोल वॉल्यूम पे फ्लूइड और प्लेट दोनों कांटेक्ट में आए. सो व्हेन दे आर कमिंग इनटू कांटेक्ट, एज पर न्यूटन्स थर्ड लॉ ऑफ मोशन, फ्लूइड के पास मास है इस बार. सो डेफिनेटली दिस फोर्स एक्सर्टेड बाय द फ्लूइड ऑन द जेट इन दिस रीजन, फोर्स एक्सर्टेड बाय द फ्लूइड ऑन द जेट इज सेम एज फोर्स एक्सर्टेड बाय द प्लेट ऑन द फ्लूइड अगेन हियर. करेक्ट? यस. नाउ लेट्स सी. सो मान लो कि मैंने कोऑर्डिनेट सिस्टम डिफाइन करा है. So this is x-axis and y-axis. This coordinate system can be anything, so I'm just fixing it like this for the time being, for some short story purpose. Then let's see sigma f on plate, or let's say in x direction, resolving in x direction. If you resolve in x direction, because normally sigma f को हम sigma fx i cap plus sigma fy j cap ये सब चीज लिखेंगे, इंजीनियरिंग मैकेनिक्स में थोड़ा सा आते हैं. So can I write this as sigma fx on plate, force acting on the plate is equal to, ये दोनों वेक्टर सेम ही है लेकिन एक माइनस साइन है, so माइनस सिग्मा fx on fluid. लेकिन अब हम फोर्स एक्टिंग ऑन फ्लूइड कहां से लाते हैं? हमने डेराइव किया था सिग्मा f on fluid is this, लेकिन यहां एक माइनस साइन भी है. so इस माइनस साइन के वजह से हम इस आउटलेट्स को माइनस करते हैं, इस इनलेट्स को पॉजिटिव करते हैं बस. ओके, ऑल नॉर्मल राइट, नो इश्यू. समेशन m डॉट इन इंटू v in at x. okay, this is at inlet minus, sorry, this is at outlet. Now first there is outlets, same expression I'm just copying. m dot out v out in the x direction minus summation m dot in times velocity at inlet in the x direction. yes or no? यहां तक सबको समझ में आया या नहीं बताओ? summation m dot in v in x and here it is minus. yes or no? please type in the chat box. 2. okay, now let's observe something. so multiply with this minus, then ultimately this becomes plus and there is a minus sign here. okay, because इस माइनस को अगर अंदर लेके चला तो this becomes minus and this becomes plus. now अब बताइए, this is the control volume what I have taken. अब इस कंट्रोल वॉल्यूम पे मतलब मान लो कि यू ट्रीट दिस एज अ सिंगल एंटिटी, कितना इनलेट्स है? बल्कली एक ही इनलेट है ना. so this is inlet, this is the control volume, this green boundary. so there is only at one point where the fluid is cutting. then how many points it's cutting exits? there are 2 exits actually. okay, so there are 2 exits. then let's call these sections as the locations where fluid is cutting the control surface as 1, 2 and 3. okay, so this is 1, 2 and 3. so these are the 3 spots where the fluid is cutting the control surface. maybe inlets or outlets, doesn't matter, but at these 3 locations the fluid is cutting the control surface. okay, so let's see. पहले outlets पे ध्यान देंगे. minus m dot out v out in the x direction. so पहले outlets के बारे में सोचेंगे. यहां एक आउटलेट है, यहां भी एक आउटलेट है, ठीक है, लेकिन इस दोनों आउटलेट्स पे x डायरेक्शन में किसी वेलोसिटी है क्या? बताओ. so let me write this as minus, now summation m dot to v2 in the x direction plus m dot 3 v3 in the x direction. Okay, so these are the two outlets. Okay, plus inlet m dot 1 v1 in the x direction. This is the expression totally. Okay, लेकिन you can observe v2x means the x component of velocity at section v2 and x component of velocity at section v3. कितना है ये दोनों? बताओ ये दोनों कितना है? v2x and v3x कितना है? 0. बढ़िया. तब at this section, let's say this is fixed, so obviously m dot 1 is nothing but if this jet area is a, anyhow jet diameter is d, you can calculate. So m dot 1 is ρav. ठीक है, so इसका वैल्यू है कि ρav. Then v1x, so v1 at this section 1, velocity of the fluid is in the positive x direction. Okay, this is the positive x, so this is also in the positive x. So यहाँ velocity ये है कि v, of course. Then if you simplify this total result, वो आंसर ये आएगा कि minus 0 plus 0, so total minus 0 plus ρav into v, which is ρav square. Got it? Normally many times people commit mistake here. They actually write this expression for sigma fx on fluid and they write the momentum change of the fluid actually. Okay, no, momentum change of the fluid is not actually equal to sigma fx on fluid directly. This minus sign is there. Okay, which comes from the RTT actually. Yes, got it? अगर ये चीज सही है तो we'll move forward. Now the theory is built for linear momentums. We'll just keep applying as many examples as we can. Okay, ये बहुत सिंपल एग्जाम्पल है लेकिन कॉन्सेप्चुअली बहुत लोगों को दिक्कत होगा पक्का. ओके, बहुत सारे लोग इसमें भी मिस्टेक्स करते हैं, माइनस डालते हैं, प्लस डालते हैं यहाँ. ओके, बट दिस इज द एक्चुअल सीक्वेंस टू गो. गॉट इट? पहले आउटलेट्स कितना है, इनलेट्स कितना है, इस समेशन लिखेंगे. ओके, इसके बाद आउटलेट्स में इस एक्सपेंशन लिखेंगे. मतलब समेशन है तो ऑब्वियसली सम आएगा, यहाँ भी आएगा, लेकिन यहाँ सिर्फ एक ही इनलेट है, सो एक ही टर्म आया था यहाँ. सो वेलोसिटीज क्या, वेलोसिटी का वैल्यूज कितना है वो कैलकुलेट करेंगे हम. मतलब नॉर्मली इफ यू हैव आइडिया यू कैन जस्ट राइट दिस एंड 0. नाउ इफ आई आस्क यू in y direction sigma fy on plate, ये कितना होगा? sigma fy on plate बताओ, sigma fy on plate कितना होगा? जीरो. ज्योतिष बहुत धूमधाम आते हैं आप लोगों को. ठीक है, कैसे है दिखाओ. So we should add negative sign by Newton's third law, obviously, because now that negative sign came from here. Okay, force acting on plate by fluid is just opposite in direction to the force acting on fluid by plate. Correct? That's what Newton's third law tells you, obviously, because the force exerted by fluid on by plate on fluid is same as this but in the opposite direction. So एक नेगेटिव साइन आते हैं. ओके, नाउ लेट्स सी 0. लेकिन कैसे है डे आउट करके देखेंगे. सिग्मा fy ऑन प्लेट इज इक्वल टू माइनस सिग्मा fy ऑन फ्लूइड. करेक्ट? ऑब्वियसली ये पता है हम सबको, विच इज माइनस समेशन. तो सिग्मा fy ऑन फ्लूइड, सो सिग्मा fy ऑन फ्लूइड बेसिकली हमने डेराइव किया था इन स्टडी स्टेट. Sigma f on fluid is summation of outlets minus summation of inlets. You can see summation of outlets minus summation of inlets. So let's do that. Summation of m dot out v out in the y direction minus summation m dot in summation m dot in v in the y direction. Okay, so let's see. This implies sigma fy on plate is equal to minus sigma m dot out v out. So कितने जगह से outlets हैं? 2 locations, 2 and 3. So इसको हम लिखते हैं कि m dot 2 v2 in the y direction plus m dot t v3 in the y direction minus sigma m dot in v in. There is only one inlet, so m dot in v1 in the y direction, of course. Okay, so ये values है आपके पास. तो ये यूज कहाँ होगा? RTT आगे टर्बो मशीन्स, ऑयलर्स इक्वेशन. विदाउट ऑयलर्स इक्वेशन यू कैन नॉट डू एनीथिंग. इतना लंबा डेविएशन इतना शॉर्ट में इतना ही होता है ना, मतलब 2-3 स्टेप्स, नथिंग बिग. वंस यू नो मैथ्स you can play with anything like this. Okay, that's why I generally play with all the derivations. Okay, once you know vector calculus in hand, it's like a क्या बोलते हैं ब्रह्मास्त्र टाइप. ठीक है, एक बार अगर लगाया तो पूरा डेरिवेशन 3-4 स्टेप्स में होगा फटाफट. ठीक है, so let's see, these are the values. Now can someone tell me, definitely if things are uniform, mass flow gets separated uniformly. Okay, मतलब मान लो कि अगर यहाँ m dot, then here it will be m dot by 2. So let's say total mass is m dot, पूरा mass m dot है, तो m dot by 2 and m dot by 2, it splits uniformly, सबको पता है. Okay, then in such case minus m dot 2, mass cutting the control surface at section 2 is m dot 2. Velocity at section 2 in the y direction. So velocity of the fluid when it's cutting, when it's crossing in the y direction is v, of course. Okay, क्योंकि ये positive y direction है, ये भी positive है, so this is v. This is v actually here. So v plus m dot 3, ये क्या होगा? ये भी m dot by 2 uniform. Okay, v3 at y. So at the third section, what is the velocity in the y direction? बताओ सब लोग. m dot by 2, what is the velocity at the y direction? माइनस v. ओके, ये माइनस v लिखना बहुत जरूरी है. क्यों? देखिए y डायरेक्शन ऊपर तक है, मतलब इट्स लाइक इन द पॉजिटिव y डायरेक्शन, लेकिन यहां फ्लूइड नीचे आ रहे. ठीक है, सो v शुड बी माइनस v. गॉट इट? If you write v here, that's wrong. The reason is the coordinate, the y direction and the velocity are in opposite directions. So एक minus v लिखना पड़ेगा. Minus इसको m dot is the total m dot. There is only one inlet. v1 at y. So at section 1, velocity in the y direction. What is the velocity in the y direction? Can someone tell me? What is the velocity in the y direction? Can someone tell me this? Zero, obviously, correct. So this is 0. Yes. Got it? क्योंकि ये दोनों टर्म्स कैंसिल हो जाएगा, बस इतना ही है. एंड फिजिकली ऑल्सो जब फ्लूइड यहाँ नीचे आता है, सो रिएक्शन फोर्स की वजह से प्लेट ऊपर जाने के लिए कोशिश करते हैं, लेकिन ऊपर भी जो फ्लूइड ऊपर जाए, सो वो रिएक्शन फोर्स नीचे तरफ से लगते हैं, सो बोथ गेट कैंसिल्ड. दैट्स व्हाट मैथमेटिकली यू कैन सी हियर. ओके, fine. So when this arrangement in horizontal plane, then both y is positive. Both y are in x direction, it just slightly smoothly glides. अगर मास इक्वली स्प्लिट नहीं होता तो नेट फोर्स एक्टिंग, नेट फोर्स आता है, मैं दिखाता हूं अभी. द नेक्स्ट स्टेप इज दैट आई विल नॉट पुट द प्लेट वर्टिकल, बट आई विल इंक्लाइन द प्लेट एक्चुअली. ठीक है, थैंक यू नित्या. लुक, अब हम जाएंगे सेकंड एग्जांपल पे. I'm fixing this plate for the time being. So अब मान लो कि फ्लूइड जाए, this is total discharge Q, density is constant everywhere. So let's talk in terms of discharge. This is Q. तो मान लो कि यहाँ Q1, यहाँ Q2. Okay, then if this is Q1 and this is Q2, if I ask you what is Q1 and Q2 or Q1 by Q2, ये ratio कितना होगा? Because if you know this, you can identify Q1 and Q2 easily. Okay, so let's say this plate is inclined at some angle theta. theta. Q1, V1, Q2, V2. We'll see what are the velocities. Okay. So let's see. This is Q1 and V1. So again, we have to choose a control volume in the location where fluid and this plate are getting in contact with each other. Correct? A1 V1 by A2 V2. अच्छा ठीक है, लेकिन V1 by V2 कितना आता है और A1 by A2 कितना है पता है तुमको? नहीं ना? 1 minus cos theta by 1 minus cos theta. So 1 is the 1 plus cos theta by 1 minus cos theta. मुझे इतना दिमाग मतलब याद नहीं है. So I'll derive now. Okay. So let's see. You take a control volume again. क्योंकि ये है रीजन जो फ्लूइड और प्लेट कांटेक्ट में आए. ओके गाइस, मेरा टीचिंग स्टाइल ऐसा है कि जब मैंने थियरी पढ़ाता हूँ उस टाइम पे लोगों को दिक्कत होते हैं, लेकिन मैं एक्सप्लेनेशन पूरा देता हूँ. ठीक है, जो बीच में छोटा सा पॉइंट्स है, छोटा मोटा पॉइंट्स है, सबको एक्सप्लेनेशन देता हूँ. लेकिन ओनली वन थिंग यू हैव टू डू इज फोकस लगा के ध्यान से सुनना है बस. ठीक है, I'll tell you one thing. Whatever the physical mistake you are doing, I've told you. People tell you that many times sigma f is equal to dmv dmv by dt, and they'll ask you to put force acting sigma f summation m dot v in minus summation m dot v out. This is what they tell you. Okay, they'll tell you that adjust this dt into this dm, like what they tell you. They'll tell you this. So dmv by dt, take mass is constant, so take this, this velocity is constant, so we can write this as dm by dt times v, and this is m dot, so m dot v, so the momentum at the inlet minus momentum at inlet. Can you tell me one thing honestly? In this complete control surface, can you guarantee that this v stays constant always? At least direction will change, no? Obviously magnitude is v, but here the magnitude is different. Many times people say this. I am even worried that many big legends, who they call themselves legends, they teach this. I'm literally surprised to hear in many platforms, of course. But obviously you cannot take velocity out as constant. Okay, and you cannot write dm by dt as m dot. दूसरा चीज ये है कि they'll tell you this is on plate. Okay, ठीक है, they'll tell you this is for Newton's third law of motion. You cannot reveal the name, even I don't want to take out the names. Listen. Sorry to laugh, but in general this happens. Look, sigma f on plate is what they tell you. They'll tell you multiply minus n with the same logic, telling you that the reaction force is opposite and all this. If you generally write this honestly, as per Newton's second law of motion. Newton's second law of motion क्या पढ़ाते हैं आपको? If you have a mass m, you apply some force F, then F is equal to dm by dt. ये होगा, correct? If force is acting on the plate, how can you take momentum change of the fluid? You should take momentum change of the plate, no? Ideally, yes or no? अरे if this marker पे मैंने 10 न्यूटन का फोर्स लगाया तो marker चलेगा पक्का. So net force acting on the marker should be equal to the momentum change of the marker itself. Then how come net force acting on the plate is equal to momentum change of the fluid? It should be momentum change of the plate ना? Yes or no? यही क्वेश्चन इस तो इंटरव्यू में आया था, बहुत सारे बार BRC में मांगा था बच्चों से. And 2 minutes silence for all such people. Did you understand the logic? If you want to write F equal to dm by dt, the force acting on the body and the mass of the body should be same. Obviously, only then you can define your Newton's second law of motion. But यहाँ force एक body पे है, momentum change दूसरा body पे है, दोनों को कैसे link कर सकते हैं? Did you understand the lock in this? Mathematically answers आते हैं, ठीक है, लेकिन अगर conceptually किसी ने question पूछा तो बस हो जाएगा. Okay, and I'll tell you one more important thing. These two things are not equal if the things are unsteady. Okay, मान लो कि जब रॉकेट जा रहे ऊपर, रॉकेट में ये मास कांस्टेंट नहीं है, वेलोसिटी बिल्कुल कांस्टेंट नहीं है, आपको पता है. सो ऑल दिस थिंग्स विल प्ले अगेन. ओके, सो प्लीज फॉलो द ट्रेडिशनल एक्चुअल फ्लूइड मैकेनिक्स, नॉट द whatever people assume it to be correct. ठीक है, ठीक है. अगर न्यूटन सेकंड लॉ डालना है तो फोर्स एक्टिंग ऑन whatever the, let's say, force is acting on some body, the momentum change should be of the same body. It's not like you apply force on me and ask momentum change of Deepthi or Omkar Chaudhary, someone. Got it? If you slap me, I only get affected, na? So there is momentum change of me, not them. That's what this explanation is actually. Fine, chalo. Q2. What is Q1 by Q2? So पहले जो continuity equation होता है उसको अप्लाई करेंगे. From continuity, rho or Q is equal to Q1 plus Q2, obviously. Okay, so mass should conserve. सबको पता है ये चीज. नेक्स्ट दूसरा चीज ये है कि यू नीड वन मोर इक्वेशन, क्योंकि आपके पास दो अननोन है. मान लो कि पूरा टोटल क्यू मैंने दिया था, सो टोटल अमाउंट ऑफ डिस्चार्ज इज गोइंग. नाउ हाउ कम इट इज स्प्लिटिंग? दिस एंगल थीटा इज आल्सो नोन. ओके, वी नीड वन मोर इक्वेशन टू सॉल्व Q1 एंड Q2. नाउ इफ यू डिफाइन ए कोऑर्डिनेट सिस्टम, सो मान लो कि यहां x है, यहां y है. ओके, नाउ I'll define one more coordinate system actually for the easiness. Let us take the coordinate system to be normal direction and tangential direction, and obviously this angle is theta, angle made by the plate with the horizontal. This tangential is parallel to the plate and normal is exactly perpendicular, n and t, of course. Okay, because force. Thank you, Babu. But one thing is, whatever the force you are applying, see, normally when you write vectors, let's say you take a force, for example, you resolve in Cartesian or in polar coordinates, the force vector remains same. Okay, like let's say if this is some axis x, y, there is some force F which you are writing. Then in such case, if you resolve this in this coordinate system, you will have Fx and you will have Fy, of course. Okay, so this is Fy. And obviously, if this is the free vector, if you move here, this is the vector addition. So F is equal to Fxi plus Fyj. Okay. Now second thing ये है कि मान लो कि आपने इसी फोर्स को पोलर कोऑर्डिनेट्स में रिजॉल्व किया था. तो अब आपका आता है कि Fr and F theta. So this is Fr and this is F theta. You will get same difference in magnitudes. The same force can also be expressed as Fr Er cap plus F theta E theta cap actually here. Correct. Now ultimately one thing this and this are not equal and Fy and F theta are not equal, but this force is same in both the cases. Physically जो force होता है वो वही force होता है, इसलिए जो governing equations होता है, लेकिन कुछ differential equations होता है वो vector form में लिखना बहुत important है. क्योंकि मान लो कि मैंने ऐसे लिखा था, ओके, इन 2D लेट्स टेक फॉर द टाइम बिंग. ये सही इक्वेशन है, लेकिन सिर्फ कार्टेशियन में, पोलर कोऑर्डिनेट्स में इक्वेशन वो नहीं. लेकिन अगर मान लो कि मैंने ऐसे लिखा था, दिस इक्वेशन इज करेक्ट इन कार्टेशियन, पोलर, स्फेरिकल, व्हाटएवर यू टेक. करेक्ट, ऐसा नो. इसलिए नॉर्मली जो गवर्निंग इक्वेशंस होते हैं वो डेरिवेशन से पूरा चीज नॉर्मली अगर आपने एक्चुअल सब्जेक्ट पढ़ा तो वेक्टर्स में होता है, नहीं तो टेंसर्स में. Resultant will be same, theta will be same, everything will be same, but the way we denote the vector changes from system to system. Okay, as this equation is not the correct equation in polar coordinates, of course. Okay, it's only valid in Cartesian, but this equation in vector form is valid in any system. Okay, that things. So these are little nice points actually. Okay, so keep in mind. Fine. Okay, so let's see. थोड़ा बात करनी थी. Yeah, you can ask, no issues, Babu. See, anytime I forgot to put my Telegram group, but I have some class notes. Okay, I'll show you. My Telegram group is the only thing. I was recently teaching maths on YouTube on English channel. So कहाँ है ये? हाँ, ठीक है. वो बंदा मैं ही हूँ. So this is my Telegram channel actually. You can scan this maybe. Okay, तो मैंने मैथ्स पढ़ाया अभी रिसेंटली ऑन यूट्यूब, मतलब पूरा नहीं लेकिन थोड़ा था, मतलब टिल डिफरेंशियल इक्वेशंस आई हैव टॉट. So this is the group actually. So इसमें join कर लो. Already there are 1500 plus students उस group में. So you can discuss whenever you want. Or else if they cannot answer your queries, I'll definitely put my hand and try to guide you. Okay. And in my class, you need not worry of asking doubts. मैं कभी भी सर आज से स्टार्ट कर सकता हूँ. पक्का स्टार्ट कीजिए, कोई दिक्कत नहीं. See, it's never late to start. You can start at any point. Okay. And in my class, लकमसानी नागा दुर्गा, मेरा नाम इतना लंबा है, ठीक है. Fine. So let's see. I'll tell you one thing. In my class, I'll never scold or I'll never shout for asking doubts. Okay. For asking doubts. कितना भी छोटा डाउट है, कोई दिक्कत नहीं. अगर सीखना है तो पूछ लो बस. I'll explain you peacefully and patiently. Okay. I'll never say that ये बहुत छोटा चीज़ है, 11th क्लास में आएगा, 8th क्लास में आएगा, 7th क्लास में आएगा, नहीं पता है. I'll never say this. Okay. Fine. चलो. Now let's solve this question then. Now net force acting in the tangential direction, acting on the plate, in tangential direction, is kitna? Again, this is the direction in which fluid smoothly slides. Okay, like the previous case. Whenever fluid is along the plate direction, then ultimately in this direction the fluid smoothly glides in the tangential direction, right? So what is the net force acting in the tangential direction? Thank you, Ash. But please tell me, what is the force exerted in the tangential direction? In the tangential direction, the fluid is just smoothly gliding. That's all. It's not interacting. Okay, there's no, once the fluid enters this tangential direction, there's no change in momentum between this fluid here and here. What is the change? Any idea? Net force acting on the plate in tangential direction is, it is actually 0. The reason being, fluid smoothly glides, no friction, nothing. So fluid smoothly glides along t direction. Along t direction actually. Okay, fluid just smoothly glides. If there is friction, then what happens? This plate will try to stop the fluid. Means normally if the fluid has viscosity, then the plate will try to stop the fluid. As a result, fluid will also try to exert some force on the plate. Okay, but in general there is nothing friction, nothing. We are not doing any frictional analysis, so that it's just smooth glidely. There is no point where the fluid and the tangent, the fluid and the plate gets into force interactions. Okay, so this is 0. So let us do the same thing. Therefore, sigma f t in the on plate is equal to 0. This implies minus sigma f on fluid in the tangential direction. On fluid is also 0, obviously. So let's see sigma f t on fluid. So let us look at the tangential fluid. So which is of course same as summation m dot in v in. Acha, this is out minus in. I always get confused between this. Okay, so normally if you take the body out minus in, so this is in minus out now. So in minus out, yeah, correct. So is correct. Sigma f on plate on fluid is minus outlets plus inlets. Yeah, correct. V in the t direction, in the t direction minus summation m dot out v out in the t direction. This is what we have. Okay, in that case mu into normal force. In that case if you have viscosity and all. Okay, but practically there should be some net force as it's trying to assist, obviously, because in practice friction has viscosity. I mean the fluid has viscosity, of course. Okay, when there is viscosity, the plate will try to stop the flow, and obviously since flow and the flow rates are not equal, so ultimately the plate experiences certain drag in any one of the direction. Okay, that's all. It's not assumption. Okay, I have shown you already. I have taken so much of scoldings from you to prove this. Okay, because of this on fluid. So you see, inlets would be negative and outlet is actually positive actually here. Okay, so it's basically outlet positive minus inlet negative on fluid. Outlet positive and inlet negative, right? Oh, sorry, here I have changed. That's why this confusion is always there for me. Unless I do the derivation, I'm not. V out in the t direction minus summation m dot in V in the t direction. Yeah, now it's fine. Okay, so I think this is the confusion. करेक्ट ना सर? कुछ समझ में नहीं आया है, ऊपर से जा रहे ये यो सब बताया ना आप लोगों ने पहले क्लास की फर्स्ट हाफ आवर में. ठीक है, कोई दिक्कत नहीं. लुक, so that's what I have told Aman already in the last case. What is the defect you have learned? I have told you. Okay, basically what people have told you, they are telling you force on one body and momentum change of other body actually. So now I hope it is correct. Okay, so outlet minus inlet for the fluid, correct now? Sigma F for, as per Newton's second law also, weight of change of net force acting on the fluid is rate of change of momentum of the fluid. So outlet minus inlet. Now this is correct, right? Yeah, that's what we have derived now, obviously in this case. So sigma T on fluid is sigma F on fluid is outlet is positive and inlet is negative. So out minus in, obviously. So let's see at how many points we have the cuttings actually. So this is section 1 where the fluid is cutting the control surface. Section 2, section 3 of course here. Okay, so section 1, section 2, section 3. Agar ye scolding hai then how? Yeah, ending should be greater than beginnings obviously. So let's see. So let's observe here summation of the outlets. 2 and 3 are the outlets. M dot 2 V2 at the tangential direction plus M dot, see always guys please make a note, whatever the direction of this force you are considering, same direction of velocity you should consider. Okay, because mass is just a scalar, it can compensate. And M dot 3 V3 T minus, now there is only one inlet, so I am just writing only one inlet, M dot 1 V1 in the tangential direction. Now let us observe certain things. If this angle is theta, means the angle of the plate with the horizontal with the x direction is theta, then let's observe if the velocity is v actually here in this case. Okay, because the jet is coming straight, so if the velocity is v, if you resolve this in the tangential direction, what is this velocity if this angle is theta? Can someone tell me? Means the jet is trying to come in this x direction, so if you make this angle theta, if you resolve this v, then ultimately you know along the tangential direction it is v cos theta, along this direction it is v sin theta, correct? Now please tell me so please tell me this m2 is m2 dot can be written as rho times q2. Okay, this is no issue, rho times q2 of course. So rho times q2, this is rho times q3 and this is rho times q1 of course. Let's or q total whatever the, oh I think I have done this as 2 and 3, right? So let's do this q2 by q3. Okay, because 2 and 3 are the notations we are using for sections. Okay, so this is q2, let's call this to be q2 and let's call this to be q3 because I am using the same notations. Okay, so q3 and let's say this is q total, so this is OQ. Now let us look at the velocities very carefully. So what about the whole negative of fluid? It is negative, but since this is 0, so I am deleting this minus sign. Okay, because negative of something is 0 will actually tell you that something whatever is 0 of course. Okay, correct na Amandeep Negi? Got it? Because it is 0, so is minus sign ka zarurat nahi hoga obviously. Minus x equal to 0 is x equal to 0 obvious. Okay, so now v2t, what is the velocity at section 2 in the tangential direction? So this is section 2. यहाँ fluid सीधा v velocity से ऐसे जाए. This is v because the total velocity will not change ultimately if this is v here, because there is no loss, no kinetic energy loss, nothing. So and the height of the plate nothing is told. So if you apply Bernoulli's equation, the kinetic heads should remain same. Okay, so velocity is same because total mass is same. So this v and this is v at section 2 in the tangential direction. What is the velocity? T is in this direction, so this v is also in this direction. Okay, so we can write it to be plus v of course. Okay, then v3 at t. So at the third section in the tangential direction, this is the velocity v, but actually tangential direction is towards upward. Okay, so if tangential is upward and this is actually downward, then what is the velocity in the tangential direction Can someone tell me? Can someone tell this? Minus V, of course, correct? Because tangential is actually positive, but this fellow is actually coming down, of course. So this is minus V. Okay, negative, minus V. Now what about this? V1 at the tangential direction. So at section 1, this is the story. So at section 1, in the tangential direction, this velocity is V cos theta. Correct? Because you are doing force analysis on tangential direction, all these velocities should be in the tangential directions. Okay, and depending on the system, basically if they're along the t-axis, they are positive. If they're in the opposite direction, you have a negative, of course. Okay, so this V cos theta I have just written here because this is along. If you resolve this, the tangential component is exactly in the same direction of this t actually. So that's why this is V cos theta, of course. So this total quantity is sigma ft on fluid is 0. Is this clear to all of you? Yes, thanks Vishesh. But please type in the chat box, is this clear to all of you? ये सबको समझ में आया या नहीं? माइनस V3 cos theta माइनस V2 cos theta इन x डायरेक्शन. ठीक है, x डायरेक्शन में दूसरा वैल्यूज आते हैं, लेकिन टेंजेंशियल डायरेक्शन में अगर कैलकुलेट किया तो ये आएगा ना पक्का. Okay, Bamashi powder. So let's simplify this then. 0 is equal to rho q2v minus rho q3v minus rho qv cos theta. इतना है हमारे पास, करेक्ट ना? Because obviously you can check like yeah, this minus v is there, so this plus into minus gives minus, so that's why I have written a minus sign here. So you can calculate density and velocity, it's common in all the terms, which tells you q3 minus q2 or q2 minus q3, maybe you can say q2 minus q3 is equal to q cos theta. This is one equation. And mass conservation से हमारे पास और एक इक्वेशन है 2 plus 3, okay, because we have denoted them as 2 and 3, so q2 plus q3. This is the mass conservation. Please correct it because at section 2 I want the discharge to be 2, 3, these things. So this is one equation or second equation, and ये है हमारा पहला equation. So solve करेंगे, बस हो जाएगा. 2 equations, 2 unknowns, फटाफट solve कर लो. Solving 1 and 2, q2 plus q3 is equal to q. A basic fun stuff, you all can do this. Then दोनों को ऐड कर लो. My writing sometimes is very bad, huh? Q by 2 times 1 plus cos theta plus q3 is equal to q. Okay, so q3 is equal to q minus of this, so this is q by 2 times of 1 minus cos theta. That's it. Yes. Okay, your writing is bad, but mine is just a bit. Engineers tend to be like that, yeah. Okay. भाई v1 v2 एंड v3 का मैग्नीट्यूड सेम क्यों है? क्योंकि प्लेट पे फ्रिक्शन नहीं है, सो इसलिए जो टोटल काइनेटिक एनर्जी ऑफ द फ्लूइड होता है एज ए बल्क वो सेटिस्फाई होना चाहिए. ओके, 1 plus cos theta by 1 minus cos theta. I got correct. Yeah, you are correct. 1 plus by 1 minus. ओके, नॉर्मली जब एग्जाम होता है ना, मुझे इतना याद नहीं होगा कि ये प्लस या माइनस. ओके, नॉर्मली मैं क्या करता हूँ, मान लो कि आपका फंडामेंटल स्ट्रांग है, 5 seconds to write this, hardly 20 seconds to write this, but carefully, or maybe let's take 30 seconds. Okay, no issue, 30 seconds you can write this. So within 35 or 40 seconds you can come up to this line, equation 1 and equation 2 you can write in 40-45 seconds maximum. solving these two takes hardly some 20 seconds. That's it. So within 1 minute I can always excuse me. So within hardly 1 minute you can get this result. Okay. V1 and V2 same QA. Which is my बोल रहा हूँ. So what are the velocity here? The fluid do not get any change in its velocity because of no friction, nothing. Okay. Okay, give me 1 second. I'll explain you. First of all, please confirm. Is this clear to all of you till this point? Yeah. Yes or no? Please type it in the chat box. Is this clear to all of you till this point? Yes or no? If this is clear, I'll explain you why V should be same. Okay. Now let's see. I'll ask you something. If you apply Bernoulli's equation, okay. Let's say if you apply Bernoulli's equation, fluid is going in this way, something like this. So let us split this into two parts. This total discharge Q which is coming, let us split this into two parts, Q1 and Q2, so that maybe Q1 is going in this direction and Q2 is coming in this direction. Okay. If we apply Bernoulli's equation, because there is no viscosity, nothing, so obviously P by OG, incompressible flow, you take, we are dealing with liquids of course for the time being. Okay, this is what you know. P1 by OG plus V square by 2G plus Z is equal to 0 or is equal to constant. Okay, because normally I'm habituated to write in differential senses, so this is constant. Now let's take, if you take a small chunk of fluid here, some small volume of fluid, this volume will travel all the way till here and it leaves. Okay. Then when this system is open to atmosphere, is there any pressure difference between this point 1 and this point 2? Someone has asked me this question, why velocities are same, so please answer me. At this point and at that point, is there any difference in the pressure if the complete apparatus is open to atmosphere? Or if you write for the small volume of the fluid, if you write at 1 and 2, then is there any pressure difference that occurs if complete apparatus is open to atmosphere? No, right? Both are atmospheres. Are we considering any? Yeah. So it cancel up. So are we considering any potential heads, potential differences here? Are we choosing any length of the plate? There is a difference of potential. Something we are doing? No, because the jet generally has very high impact velocity, and normally in turbo machines it's extremely high, of course. But normally compared to the kinetic heads, the potential heads are much small. Okay, in this particular case. So whatever the velocity of this guy here, same velocity all over. If there is no loss, if there is loss at some location, then velocities will change because of the friction on the surface of the blade, all these things. But in general, if nothing of such friction, these things are there, velocities has to be same. Okay, fine. Energy should conserve, na? Obviously, that's what. So it's frictionless, na? Of course, that's why we haven't taken this HL. No, I am telling if there is friction, then this HL will come and then these two will not be equal. There is some difference between them. Okay. Yeah. Okay, fine. So let's solve this question in a different, okay, fine. So this is clear, I hope. Y velocity should be same. Then let's see force exerted by the jet in x direction. Okay, for this case, let's calculate that. Force exerted by the jet in x direction. So let's solve this. If you see carefully, sigma fx on plate by the jet on plate. Okay, let's be specific. On plate in x direction. On plate is equal to minus sigma fx on fluid so minus of this fluid, minus is out by minus in, so this is sigma m dot out minus in, so in v in the x direction okay. So let's see again 3 points, obviously 1 2 and 3. So there is only one inlet. Why? Anitya, why Nitya? आज fast रखना पड़ेगा. We want to close fast. Okay, maybe आज इतनी तक है सर. Okay, just I'll finish this force calculations and we'll close. Okay, I understand it's hectic क्योंकि ऐसा पुराना किसी टाइम पे आपने. How many of you learned all these things for the first time in this class? Tell me honestly. Honestly, how many of you have learned all these things in this class for the first time? Anyone? Oh, a lot of a big goal is there then. Okay. Reynolds transport theorem applying angular momentum. Of course, angular momentum we'll see tomorrow maybe. Okay. पढ़ा तो पहले भी आज सब क्लियर हो गया. Okay. मैं तो आज आया हूँ. Okay, in college. Okay, great. So let's see. Yeah, it's okay. Great then. So let's see, guys. Let's calculate this. What we are talking? We are talking about this force m dot v out x. Okay. So let's see. There is only one inlet. M dot 1 v1 in the x direction minus there are a couple of outlets. Multiplication. Okay. But misconcepts clear today. Okay, good. So let's see. In the m dot 1. So m dot 1 can be written as OQ obviously. Okay. Because this m dot 1 is the total mass which is flowing in. So OQ into v1 in the x direction. So what is the velocity at the inlet in the x direction? So in this direction x. So ultimately is the x direction. So that's x of course. So this is v ultimately. Okay. Minus m dot 2 rho q2 into v2x. So what is v2x of course? Okay. So v2x is of course v2x is at 2 this section. This is v. So ultimately the velocity in the x direction is how much? So this angle is theta. So v cos theta is the x component of velocity in the positive direction. So this is v cos theta plus m dot 3 rho q3 into okay. So rho q3 into v3x. So what is v3x actually? Let's see. So at this point the velocity is in this direction. So if you resolve this in the horizontal and vertical directions, this angle is again theta, right? Because the plate and horizontal is theta. So this is theta. So ultimately this is v cos theta, but it's in the negative direction because positive x is towards right, but this v cos theta is towards left. So minus v cos theta. This is what you have. Okay. So let's simplify these things then. Rho q, this q2 can be written as q by 2 into 1 plus cos theta whatever. So rho qv, if you take common 1 minus this term, this q2 can be written as q by 2 into 1 plus cos theta, correct? So q2 is q by 2 into 1 plus cos theta. So let's write this as q by 2 into 1 plus cos theta. So this would be 1 plus cos theta into cos theta by 2. Correct? That's what you have because this q2 can be written as q by 2. So this rho qv can be again taken out. Then minus of this minus. See this minus of this minus plus then q3 is 1 minus q by 2 into 1 minus cos theta by 2. So 1 minus cos theta into cos theta by 2 of course. Okay. So this is the simplification what you have to do. So if you simplify this rho qv into, so clearly you can observe this plus 1 by 2. Okay, maybe let's simplify one more step. 1 minus 1 into cos theta by 2 with a minus sign. So cos theta by 2 minus cos square theta by 2. Then this is plus half plus cos theta by 2, of course, minus cos square theta by 2 actually. So if you simplify this, minus cos square by 2 minus cos square by 2 is 1 minus cos square. So this gives you rho qv into 1 minus cos square by 2 minus cos square by 2. So this minus cos square by 2 and minus cos square by 2 gives you a cos square theta. So 1 minus cos square theta is sin square theta, which you all might have studied this. The same thing without doing this much of trigonometry, we can still get easily. Like, look, I'll tell you. Sigma Fn on plate is equal to, let's do, the job will be much easy. Sigma Fn on plate is equal to minus sigma Fn on fluid. So this can be written as sigma m dot in V in the n direction, normal direction, minus sigma m dot out V out in the n direction, correct? So ultimately there is only one inlet, m dot 1 V1 in the normal minus m dot 2 V2 normal plus m dot 3 V3 normal actually here. Okay, so this is what you get. So let's see m dot 1 rho q into V1 in the normal direction. So look, obviously we have done something here. So this is V. So in the normal direction n, it is V sin theta. Okay, so this is the normal direction velocity component at the inlet, because this is the normal direction. So this is also exactly the same direction. So V sin theta. So let's see. V sin theta. Okay, so this is what you get. OQ V sin theta, of course. Okay, something is missing. OQ V sin theta. Here something is missing actually here. Let's check. OQ V into V sin square theta is coming now. 1 minus cos square theta. This is correct, right? This is fx. Okay, fine. So let's see. This is OQ V sin theta minus. Then what is V2n and V3n? Can someone tell me? V2n and V3n. At section 2 and section 3, fluid is just moving tangentially, correct? In the tangential directions. So what is the normal component of velocity there at section 2 and section 3? You can check, like at these two sections, at this section 2 and section 3, what is the normal component of velocity? So normal is basically in this direction. Okay, this is along the tangential. So what is V2n and V3n? Come on, please tell me in the type in the chat box. 0, correct? So V2n and V3n are zeros, of course, because at location 2 and location 3, the fluid is cutting the control surface pure tangentially. There is no normal component of velocity. Okay, so we can see this is 0 and this is 0. Sigma Fn on plate is equal to rho qv sin theta, of course. Okay, now if you have this, then observe carefully little. This is the x direction. You know force in n. If this angle is theta, what is this angle? What is this angle? What is this angle actually? Can someone tell me? Angle between x and n, normal direction and the x direction. So come on quick, what is the angle? 90 minus theta. This implies, can I write fx as Fn cos 90 minus theta, which is sin theta? Yes or no? Can I do this? Because if you just resolve n onto the x axis, the angle between those two is 90 minus theta. So fx is Fn cos 90 minus theta, which is Fn sin theta, of course. Correct? So to this fellow, you multiply one more sin theta. which is the same expression even you have calculated using in the x direction balance, but here a bit of trigonometry is done. That's it. Okay, that's why choice of the coordinate system will sometimes, not sometimes, many times reduces the size of the solution actually. Is the resultant of tangential and normal direction is in x direction? No, here the plate is fixed obviously. Okay, it's not like resultant of tangential and resultant of normal is in the x direction. No, need not be. V2n and Vnn velocity is 0. Q, not V1n and V2n, V2n and V3n, because in this case at this point 2, section 2, fluid is moving pure tangential, so normal component of velocity is 0. Similarly here. Okay, if force is acting in the x direction, what is the y direction component? 0. That's it. Similarly. Got it? So Nitya, what I am telling is, whatever the sigma fx you calculated using this technique, because you know this is in the x direction is this into sine theta because of resolution, so the same answer you got even in this analysis in the x direction obviously. Okay, rho q v square sin theta होगा ना, rho a v square theta होगा. If you write q as a v, then rho a v square आएगा. ठीक है, लेकिन जब q होता है एक ही v आता है. ओके फाइन, ये V2 होगा ना, कहाँ V2 या V1, मैग्नीट्यूड ऑफ वेलोसिटी इज सेम ना, बोथ. दैट्स व्हाट आई हैव रिटन. या इज दिस क्लियर टू ऑल ऑफ यू? डिड यू ऑल अंडरस्टैंड? बेसिकली मैंने आपको सिग्मा एफएक्स दो तरीका से दिखा था, एक यूजिंग सिग्मा एफ1. okay, so sigma fn calculate किया मैंने, so as per accordingly since I am using force in n direction, velocity components are in n directions. okay, so मैंने resolve करके दिखाया था, लेकिन सीधा x direction में calculate करके भी दिखाया. दोनों एक्सप्रेशन सेम ही आते हैं, आना चाहिए एक्चुअली, अदरवाइज इट्स रॉन्ग. फाइन, एक कंफ्यूजन दिमाग से हटाओ. मान लो कि ये x है, ये y है, ठीक है, और ये fn है और ft whatever और टेंजेंशियल डायरेक्शन, और ये नॉर्मल डायरेक्शन. मतलब मान लो कि ये नॉर्मल डायरेक्शन है. ये चीज ध्यान पे रखना, ये दोनों का रिजल्टेंट ये नहीं होगा. ठीक है, मान लो कि इस दोनों सिस्टम्स का, मान लो कि देयर आर फोर्सेस fx fy, ओके, देन इज सेम एंड द रिजल्टेंट इज समथिंग लाइक दिस f. तब ft एंड fn ऐसे आएगा जैसे ft और fn का रिजल्टेंट भी सेम f होगा. वैसा कंपोनेंट्स रिजॉल्व होते हैं. t और n का रिजल्टेंट x नहीं होगा. ठीक है, दैट्स जस्ट ए कोऑर्डिनेट सिस्टम टू स्प्लिट द वेक्टर इनटू कंपोनेंट्स, दैट्स ऑल. रिजल्टेंट सेम होना चाहिए दोनों कंपोनेंट्स का, दोनों सिस्टम्स में. क्लियर कनिष्क जतवा? बस यही चीज है. सो कल हम थोड़ा सा फन स्टफ करेंगे, इस प्लेट को मूव करेंगे. ठीक है, सो अब तक प्लेट ऐसे बैठा था, सो लेकिन प्लेट को थोड़ा सा मूवमेंट देंगे कल. टर्बो के नोट्स बनाने के लिए कुछ टिप्स है प्लीज. To be frank, like the first couple of lectures maybe is like general, okay, like the basic stuff what we do like this. I'll teach you all these things. Of course, in tomorrow's class we'll go for angular momentum and sprinkler questions we'll solve. Okay, then I'll do dimensional analysis and we'll try to define some basic terminologies like hydraulic efficiency, manometric efficiency. Okay, of course, wheel efficiency. We'll discuss these things, and I'll maybe I'm not sure, but if time permits, I'll go till कल प्लेट को भगाएंगे. हाँ पक्का. ओके, so we'll make the plate move. So and I'll, if time permits in tomorrow's class, I'll teach up to Pelton wheel. Okay, Pelton wheel का एक अच्छे सा डायग्राम बनाएंगे, तो सब सॉल्व करेंगे. देखना है एक बार सैंपल. ये कौन है? ये मैं ही हूँ. So I hope you all have scanned this. I'm deleting this. So normally Reynolds transport theorem का derivation मैंने किया था. Normally in my fluid mechanics classes, control volume analysis. तो इसके बाद ये सारा plates, all these things. Okay. हाँ, यहाँ एक चीज़ मैंने भूल गया था. If theta is 0, मान लो कि ये थीटा 90 है. ओके, नॉट 0, सॉरी 90. सो प्लेट ऐसा है. सो व्हाट विल बी Q2 by Q3? टेल मी. The launch sprinkler will be covered here too. No need. If you don't need, I'll skip. I'm happy to skip always. I'll skip. I'll directly start dimensional analysis and start turbines if you are comfortable with angular momentum, launch sprinklers and all. Yeah, then in such case, if theta is 90, these two are zeros, cos theta and cos theta are zeros, it's 1 by 1, 1. So jet will be split into equal halves. That's it. Q2 equal to Q3. Okay. उसी एनालिसिस हमने करवाया था. फाइन. You have studied that? Okay. Please deal angular momentum. Okay, ठीक है, कोई दिक्कत नहीं. I'll deal. Okay. Again, using same Reynolds transport theorem, but there slightly the things change. We'll see first of all the plate when it's moving, of course. Okay. So when plate is moving, then we'll slowly start with angular momentum, of course, and then we will. आप लोगों में कितना लोग गेट एक्सी देने के लिए सोच है अभी? ओके. इतना ज़्यादा लोग. बढ़िया. गुड. फाइन. इट्स ओके. या तब भी है सर, ऑल ऑफ यू ना, ऑब्वियसली. ठीक है. PSU फोकस्ड, सो नो एक्सी. गुड. बढ़िया. लेकिन PSU जाना तो भी इंटरव्यूज में ये सब चीज़ जानने की ज़रूरत है नॉर्मली इफ दे आस्क यू. फाइन. ओके. सो हाँ, मैंने थोड़ा सा सैम्पल दिखाता हूँ एक्चुअली. So all this is Newton's third law of motion, all these plates. So you can see हमें प्लेट को भगा दिया यहाँ u velocity से. Then some questions, nice questions we have solved. Plus RTT, all these things. So normally Pelton wheel का अच्छा डायग्राम दिखाता हूँ मैं आपको. This is all thermodynamics when I was teaching thermodynamics. Then Vijay batch I have taught applied thermodynamics, I think. These are the basic terms tomorrow जो मैं देता हूँ आपको. ओके. डायमेंशनल एनालिसिस यही है पेल्टन व्हील. बढ़िया है ना. some nice diagram no of Pelton wheel. Of course jets मैंने थोड़ा ununiformly divide किया था लेकिन correct, looking colorful. So we'll draw one tomorrow and we'll go accordingly. मस्त है ना. कल भी बनाएंगे ऐसे डायग्राम. ठीक है. मतलब अगर टाइम परमिट. सी आई डोंट वांट टू रश. नॉर्मली आई लुक फॉर यू नो टेकिंग more classes but teach things in clarity. Okay, because at the end of the day completion of syllabus all this is something different, but having enough idea on the things is also important. ठीक है. so आज हम यहाँ तक आते हैं. मैं प्रैक्टिकल क्लास में देखूँ कॉलेज में. हाँ, HPCL के लिए कुछ टिप्स. स्पेसिफिक क्वांटिटीज टुमारो सर. पहले डायमेंशनल एनालिसिस करता हूँ. डायमेंशनल एनालिसिस से स्पेसिफिक स्पीड, स्पेसिफिक यू नो स्पेसिफिक स्पीड का कॉन्सेप्ट आता है, स्पेसिफिक पावर, ऑल दिस थिंग्स. सो विल डू दैट इन डायमेंशनल एनालिसिस. वंस वी डू डायमेंशनल एनालिसिस आई कैन डू. सी यहाँ भी मैंने डायमेंशनल एनालिसिस किया था. यू कैन सी. नो, दिस आई हैवंट डन हियर बिकॉज आई हैव ऑलरेडी टॉट देम इन बेसिक एक्चुअल डायमेंशनल एनालिसिस इन फ्लूइड केसेस. तो आपने इंग्लिश बैच में मत भी पढ़ाया है. You want me to be in Hindi batches, but actually in English batches I teach 4 subjects almost. There's a tight schedule clash. Like maths I'll teach for English batch. Complete maths I have finished. Normally थोड़ा सा numerical methods balance है, देखना पड़ेगा. Then fluid mechanics I teach them. turbo is of course included normally. This is the first time I'm teaching only separate turbo has a different subject, okay, but normally I teach it with fluid mechanics, of course, then thermodynamics, applications of thermodynamics. These are the things which we teach, okay, normally in English batches. So English batches में बहुत time होता है. Heat transfer आप लोगों क्या after in PWA I did not take obviously. 14 से हमारा new subject start हुआ है, yeah, of course, okay. Today and tomorrow I have these 2 classes, then after we'll. So HPCL में मैं थोड़ा सा टिप्स देना चाहता हूँ. 1 minute बेसिक डायमेंशन एनालिसिस करवा दिए है शिवम सर, ठीक है, कोई दिक्कत नहीं, वी कैन डू, नो प्रॉब्लम. सो now coming to HPCL, I'll just speak something. Normally if the pattern did not change, because I have written 3.5 years back maybe, so if trend has not changed, then it's like 170 questions, 85 non-tech and 85 technical, and I think 150 minutes is the time, correct? 170 questions and 150 minutes, as far as I remember. So if that's the trend, of course, now then selection deciding or like in rank deciding or selection के लिए ज़रूरत ये पड़ेगी कि नॉन टेक्निकल पार्ट का, क्योंकि टेक्निकल पार्ट में इतना ज़्यादा दिक्कत नहीं होगा आपको. मान लो कि आपने गेट के लिए प्रिपेयर हुआ है या किसी ESC PSC के लिए प्रिपेयर हुआ है, तो टेक्निकल में इतना ज़्यादा दिक्कत नहीं आएगा आपको. लेकिन जो लोग एप्टीट्यूड को फटाफट करते हैं, सो उन लोगों को थोड़ा सा एडवांटेज मिलेगा, ठीक है. तो अगर बुक्स की बात करेंगे तो ऑब्जेक्टिव मैकेनिकल इंजीनियरिंग बाय आर के जैन, ये बहुत बढ़िया बुक है. I don't get any money from them, but I'm just telling it's a nice book, you can follow आर के जैन. और RS को भी ऑब्जेक्टिव मैकेनिकल, ये दोनों भी अच्छा है एक्चुअली, सो यू कैन डू दैट. एंड मैथ्स के लिए आई मीन दिस एप्टीट्यूड के लिए आई थिंक RS अग्रवाल इज गुड. या RS अग्रवाल लेके कुछ क्वेश्चंस प्रैक्टिस कीजिए. गेट के लेवल पे एप्टीट्यूड नहीं आएगा, आसानी आएगा, लेकिन थोड़ा सा मतलब थिंकिंग फास्ट करना है ये चीज़ों के लिए. RS अग्रवाल से कुछ क्वेश्चन सॉल्व कर लो, ओके. This could be fine, I think. ठीक है. So चलो then we'll wind up for today. Maybe it's so much load. This basic terminologies and all I'll discuss tomorrow maybe. So then we have in today's class seen RTT. No, before that, what is a turbo machine basically, of course. Classification. Then we have talked about RTT and application for linear momentum. Okay, so these are things we have seen, and breaks will be given in evening classes. Generally मुझे breaks देने का मतलब इतना ज़रूरत नहीं पड़. I don't think we should have very breaks and all, okay, but anyway, if you want I can give some 5-10 minutes, we can have some nice common talk, then we can again continue, okay. Any book recommendations, sir? RK Bansal will do very good for this fluid machines, to be frank, at gate and ESC level, but अगर आपका थोड़ा सा मतलब hydraulic machines के लिए, लेकिन टर्बोस का मुझे टेस्ट सब चीज़ों में थोड़ा सा ज़्यादा आइडिया लाना है, तो SM Yaha is a good book, okay. Compressible flows by SM Yaha. And again, hydraulic machines, any I think RK Bansal is much more enough, okay. Yeah, so thank you all. I hope you all felt afraid in the first half an hour, then after slowly getting the idea, okay. जब मैं theory पढ़ाता हूँ उस टाइम पे सारे लोगों को दिक्कत होता है बहुत, मतलब मैथ्स थोड़ा सा कॉम्प्लिकेटेड दिखते हैं, लेकिन अगर उस लेवल पे पढ़ा है तो एप्लीकेशंस बहुत आसान होगा, ओके. ठीक है. सो कल मिलेंगे, कल 7 बजे पर मिलेंगे, और I'll move the plate. Then in this case we'll have vanes, all these things, okay, velocity triangles, of course, all these things, okay. यहाँ only. So थोड़ा notes बनाने के लिए time देना, ठीक है. I'll try to give that. Thank you to be here on English. Thanks Swati. Yeah, good night all of you. Please submit feedback before you leave, okay. So feedback का एक option होगा waiting बोल के, so उसको submit करके जाओ, ठीक है. If you have negative comments also please write, I'll try to rectify, okay, no issues. Thank you all, then take care. We'll meet tomorrow at 7 PM. Thank you all. Yeah.